Hi, everyone. I'm Sam Shan. I'm a data scientist with Callon Petroleum's subsurface technology team. Thanks, Matthias, for inviting me to talk here. With Matthias giving me credit for a lot of these slides, it's had me really racking my brain trying to think about who I stole them from to begin with. Yeah, I'll pass that along if it ever occurs to me. Yeah, I'm going to talk to you a little bit about a method I've been developing around estimating the initial reservoir pressure for individual wells using the data, using flowback data. An interesting thing happened to me when I sort of reoriented my career a few years ago toward data science. Most of my background is in reservoir engineering. When I really got focused on data-driven methods, and as nearly any data scientist in E&P is doing, I was looking for data-driven methods that also comport with the known physics of a given reservoir system. So as a data scientist, I wound up doing actually a lot more reservoir engineering than I had, and most of the time that I was called a reservoir engineer. And in particular, it seemed to point me back to RTA a lot. And it occurred to me that, and this audience will appreciate that among highly data-driven methods that acknowledge and are guided by known system mechanics, sort of all roads lead to RTA. That's been a really interesting discovery for me, and I've wound up spending a lot of time doing RTA as a data scientist. That surprised me. What I wanted to do, the reason for this development is I wanted to develop, well, it's part of a major project of integration of data at Callon through the whitCon API, where we want to populate, and it sounds like a lot of people are doing similarly. We want to populate all the inputs that we can into whitCon so that the engineers can just log into whitCon and all of the inputs necessary, the production, the petrophysical parameters, and the initial pressure and everything is all in there. It's universally covered. It's available in a nice, clean format. And there's minimal engineering staff hours required to get to good diagnostics of aggregate and contacted oil in place. So for that reason, it was really critical that whatever I come up with be totally zero touch, and be totally automation friendly. So that's sort of the objective that I started out with. And thinking of the value case, I kind of always include this slide as a best practice. Whatever the context is, whatever area of study we're looking at, I always try to start by framing the value case. And I think everybody understands really that the value case for diagnosing initial pressure is that it's a very sensitive input for RTA. And by better quality inputs, we have better quality diagnostics and ultimately better decisions. But I'm thinking specifically of, obviously this is probably most useful. Well, it's probably very useful everywhere where there's any sort of uncertainty about the initial pressure. But all of us seem to be facing a similar issue of increasing proportions of our remaining inventory being affected by parent depletion. So understanding specifically what sort of pressure that we drill into and how that affects the well results and the economic outcomes seems fairly critical. So again, wanted to be able to diagnose initial pressure on a very broad basis across all of our operated horizontals. So no conversation about this topic would be complete without acknowledging an established method that was put forward by Stephen Jones and a few other authors back in 2014. This existing method seems to work very well. It relies on an analysis of declining well flowing pressure during the flowback, and this also relies on hourly data. But it's notable for its requirement for single phase water only production prior to the well beginning to cut hydrocarbon. In most places that I look with modern pad completions, increasing well counts in co-completed packages, and longer shut-ins on average across those pads, starting to meet more frequently some of the conditions that the authors in this paper note make it incompatible. There's also confounds from artificial lift interference and frequent choke changes that are fairly common to see in modern completions. And here's an example of that. So this is an example. This is a single well that I'll sort of hold to throughout my demonstration of the method that I'm using. And it's pretty typical of what I'm seeing in terms of flowback data for our wells. This one cuts hydrocarbon in the first few hours. There's no real clear trend in the behavior of well flowing pressure as you approach that time where we initially cut hydrocarbon. So there's no flat region in the well flowing pressure profile as the Jones method requires. And so I had to come up with an alternative. And that alternative is, and I guess I can say that this entire method is broadly part of a series of ideas and build-outs that are in this suite of products, data-driven products that rely on Whitson's automatic calculation of bottom hole flowing pressure. So since we have that, I thought about an alternative, and the idea here is to rely on our classical understanding of IPR behavior. Inflow performance relationships should establish slopes through rate pressure data points. And the thinking there is that I should be able to sample groups or pairs of those data points and perform some sort of regression analysis that as you decrease in delta time between the data points, because you can see the way the slopes and or the intercepts fall over time. So as you regress toward delta time equals 0, the slopes ideally should converge on something, let me see my cursor? Something sort of like the true initial IPR slope. And since you have that slope, and since it passes through those early data points, you should be able to extrapolate through that slope back to Q equals 0 and establish a pretty good estimate of your initial reservoir pressure. So here's how that looks with real data points. These are the same well I showed you before. This is the typical pressure versus rate plot for IPR relationships, except that I've colored the data points by time. So increasing days on production shifts toward the red, and essentially what I performed here is a sample of pairs of slopes. The only filtering that I applied is that each pair has to fit our understanding of IPR relationships. So it's got to have a positive delta time, and that has to result in a negative slope. There is some noise in the data, and the more I think about this method, the more I sort of understand that there are a lot of sources in the noise. So that filtering method seems pretty natural to include. So for each pair of slope, I'm recording a slope, an intercept, a time, and a delta time. Again, with the thought being that as delta time goes towards 0, I should get a pretty clear indication where the window of intercepts would narrow toward the initial reservoir pressure. So now I'm going to shift. These aren't rate pressure points anymore. These are the actual samples. So nothing in life is as simple as we expect. I think somewhere in about this phase of the concept, I said the worst thing you can say, which is, it ought to be easy. Never say that. Yeah, what resulted actually from all the aggregation of this data is that there's not exactly a clear indication as you regress through delta time. My hope had been that left-hand plot, which has the resulting intercepts from all those samples on the y-axis and delta time on the x, I sort of thought that should have been almost triangular shaped and point right to an initial pressure. But what I find instead is that it's pretty chaotic. And as I colored it by time, you can see the graded behavior. Again, just looking at the left-hand plot, those green points that are along the top that's your early time, and the red points along the bottom is your later time. So early times are definitely pointing to higher intercepts, which suggests, as you can see in the right-hand plot, that as you get later and later in time, the slope samples are pointing to lower and lower intercepts. So that's acting more like, I forgot to sort of reinforce the point, that's acting more like boundary dominated flow, where you have declining intercepts, at least according to classical conventional IPR understanding. And my expectation was that during transient flow, you should really only see changes in the slope. But according to this, we are seeing changes in the intercept as time goes on. And in both charts, yeah, you can see the graded behavior by the other parameter. So in terms of potential causes for this, again, there's a lot of sources of noise in the data. There's quite a bit of discretization in the hourly collection of the data. So there's rounding error, there's measurement error. But assuming this reflects the true behavior of the reservoir, which I think it does because I see it in every well that I try it so far, it seems like there must be some physical causes. So I think those are probably pretty intuitive to suspect. What I have in the list here is, well perm and cleaning up changes as your water-oil ratio is changing. Clearly might be some geomechanical changes and other pressure-dependent perm and frac conductivity changes early in the life like this. There's the consideration of heterogeneity, which I've heard a lot of interesting focus on today. And whatever else. I leave that question mark out there to imply that I definitely haven't thought of everything in this method. Really, to be totally transparent, is only a few days old. I guess a couple weeks old at this point. So really putting this out there for the community. I'd love to get feedback and questions and suggestions for improvement. But yeah, the clear lesson getting to this point is that I can't infer initial reservoir pressure just looking at the intercepts and delta time alone. So what I do is, here's another view of the same data. This is the exact same data and the same trends, but it's a different visualization. So by taking kernel density estimations, you can see a little more organized, a little cleaner behavior. These kernel density estimations, if you're not familiar, are just sketches of the likely distribution shape. So through delta T here, and we're looking at intercept again, you can see organized behavior that unfortunately does not converge. My hope had been that at lower delta T's, you have a very narrow shape, indicating a clear choice for initial reservoir pressure, but it doesn't exactly converge. And you can see here when it's colored by, this is discretized to half a day or so. You can see that across the producing time, yeah, it's definitely indicating lower intercepts at later times. So made a few changes to the method here. Pretty clear to me that I need to regress on both time and delta time as determinants. I also switched from intercept as a target variable to slope, and I'll show you why that is sort of in the result here. Yeah. So here is a view of that regression. Delta time and time on the lower axes there, the X and Y, and slope on the target axis, the vertical axis there. And this is the same data. These are the same scatter plots, just viewed in 3D from different angles. So I've colored these by time, by producing days, so that you can see sort of the organized trends as they shift. And maybe particularly in the right-hand plot, you can see the trending convergence as you decrease in delta time. So that's the behavior that I was looking for. Again, now I'm looking at slope, not intercept. So this adds another step after I've concluded on a most likely slope, where we'll have to extrapolate along that slope back to the Q equals 0 of the pressure intercept. Yeah, and what you're seeing there in the purple planes is quantile regression, when you have a 2-parameter regression, you can plot that as a plane, not just as a line. So that's essentially is a very straightforward linear regression, except that it's not regressing to the mean, it's regressing to the P50. The reason for that is, and you can see in the data some heteroscedasticity. You can win Scrabble with that word, by the way, one of my favorites. All I mean is that the variance here doesn't look exactly like the variance here. One way to correct for that is to use a quantile regression. That's working out pretty well here. The error is balanced around that regression plane. The other, and I noted this, it doesn't make as pretty a visualization, but in practice, the result seems to be better if you regress on the log of slope instead of on the slope, and that helps to balance the error. And you can see there the arrows point to what we're looking for, which is what I'm calling the most likely early time IPR slope. So it's as time goes to 0, delta time goes to 0, you find the corner point of that plane, which is that linear regression equation with time and delta time at 0. That is your most likely slope. And then the final step that necessitates by when you regress on a slope is to take that slope and apply it to the data points. In the left-hand chart, that's what I've done. You don't actually have to do this with all the data points. I've done it here for the sake of visualization, just kind of so you can see conceptually we're going from the data points along that slope back to the pressure axis. And what you're looking for is the maximum. I make a note here in the script for this. I have it set up to flag that diagnostic if there's a big difference between P99 intercept and the max intercept, in case you have some highlining well-flowing pressures that might be bad data or outliers somehow. So yeah, you take that maximum along the pressure axis and diagnose that as your initial reservoir pressure. I port that over to the right-hand chart where I've reoriented the slopes and, you know, sort of along the sort of behavior you would expect from conventionally understood transient IPR, where only the slopes change and they all converge back at the initial reservoir pressure. And if you sort of walk along the color scheme there, you can see that it mostly fits. It's mostly declining slope over time, which comports with our understanding of physics, with our understanding of IPR behavior. The method itself remains agnostic to whether it is declining slope or declining intercept, but it does give you a sound diagnostic of initial pressure based on the data, and it's automation friendly. Here's an example of the method applied to a couple of co-completed wells in the same target. These are neighbor wells within the same co-development. And in the left-hand plot, you can see the well that was closer to a parent. Now, it was spaced off of the parent to what we considered an adequate distance to make the well meet our economic thresholds. But you can see the diagnostic points to about 800 psi or so difference between that well close to the parent and the interior well that's its neighbor in the same zone. And you know, you might look at these and you know, I certainly, as I worked through this, I looked at these, and based on my background, I still kind of think like an asset engineer. I looked at this, and you know, with my extreme pragmatism, I went, is this method too much? You know, is this overkill? I probably could have just looked at this data and kind of drawn a line, and I could have just, you know, sort of seen that the points vaguely correspond to an initial pressure that I could have intuitively picked very closely to what we diagnosed here. I could have done a few things like that. But again, going back to the original objectives, it has to be automation friendly. And for it to be automation friendly, you know, if it's right 90% of the time, that's not good enough. It has to be right, basically, you know, right, let's scare quotes here. It has to be an acceptable answer, basically all of the time. So far, everywhere I've tried this, it works. And the resulting Square root material balance time diagnostic plot in RTA seems to validate that. Anywhere that we have a high degree of certainty about the initial pressure, it seems to agree. I get very well organized trends on the RTA diagnostic plots. On the square root time plot, I tend to yield 0 intercepts. So generally, I'm growing in confidence that this is a sound diagnostic of initial pressure. So thoughts on continuing development. I'm regressing on P50 through the slopes. Is that the absolute best way to get to the most likely true slope? I'm not 100% sure. I'm experimenting with some other methods that may follow modal behavior a little bit better, even better. But for now, the P50 seems to do okay. I just want to spend more time testing that against the defit diagnostics and other hard pressure data where we have it. The P99 comparison to the maximum, I think there's probably better methods I can use for outlier filtering, although I haven't run into very many problems with that yet. I'd like to denoise the data by collecting slopes through groups of points instead of pairs. I think I can group those by time and delta time now that I know those are the determinants. So I think that might simplify the analysis a little bit. I'm really curious if there's a way I can adapt this to daily data. So far I can't do it just on daily data, but I think there might be a way to generalize to nearby wells that only have daily data if I have 1 or 2 wells that have good hourly flowback data. It occurred to me kind of toward the end of this that there might be more we can learn from this. You know, I set out in the beginning just to diagnose initial pressure where we're not too sure about it. But, you know, especially in some of the discussions this morning, I'm really ramping up my curiosity about transient IPR behavior in unconventionals. And I know there's some literature out there about it, so I'm going to be tuning up on that. And one of the questions I had earlier today was, are you just using raw time versus superposition time? And I am. And the purpose in that is that I always start with the very simplest viable model that I can use. Simplicity tends to yield availability, is my experience. But, you know, the only thing we're missing here to go full circle from this method back to you're just doing RTA is the initial pressure and the superposition time. So interesting to see, though, going forward, if there's more we can learn about transient IPR behavior in these reservoirs. I'd like to share my code with you. I have a GitHub repository for those of you that are coders set up. I'm adding, it's not out there yet, but I'm adding a Python-based notebook file that walks through the analysis and all the visualizations that I've shown you. And as I continue development, I'll keep that updated. Trying to make that notebook readable even if you're not a coder. So if you're curious about this, it might be worth checking my URL there. Later, I'm going to add a quick tutorial on how to put this into automation without any fancy automation tools. And yeah, pull requests, collaboration, feedback is all encouraged. That's it. Thank you.
So in one of your slides, you showed the change in intercept, and you are looking for a reason, and you put question mark, right? Why it is showing a BDF type of behavior there. So the question is, could it be because you are seeing the first crack interference? In other words, that's the start of the transitional flow, right? As you know, BDF happens when all the cracks interfere at the end of the transitional flow. So could that be the reason here?
I think so. Yeah, the question was, could frac-to-frac interference in the early time be affecting that intercept? And absolutely. I sort of tried to cover that in the heterogeneity bucket. And what I'm picturing is maybe you don't have nice, clean bi-wing fractures evenly spaced along the wellbore. But I 100% expect that to be one of the valid sources of that intercept behavior. Thank you.
Hi, thank you for the presentation. When is the pressure that you're trying to calculate? Because you have the reservoir pressure and you have the overcharge pressure after factory. What's the number that you're trying to measure here? And how do we know definitely that we
Initial reservoir pressure is what I'm looking for. So one interesting part of this, one curious part of this is that I'm ignoring the total fluid, I'm ignoring the water, and part of that is that the assumption that the oil is flowing. So we are looking at the oil inflow performance relationship, and so that oil, if you were to assume that the water-oil ratio and the real perm-effects are somewhat constant, then that oil should point back, at least in my understanding, to the initial reservoir pressure. I'm assuming that the frac charge exists mostly in the fracture space, whether that's propped or unpropped, and quite a bit of that charge is getting leaked off while the well sits as the pads continue to be completed.
maybe I'm missing something here? Because if you're looking for reservoir pressure, initial reservoir pressure, and that's overcharge pressure after factory, even your points, your terminal pressure, initial terminal pressure measurements be above the point that you're capturing, that your slope shows that you're looking for higher than you have that.
So they are. This slope has to be negative. And you're extrapolating, you can ignore, I'm sorry, you can't see the cursor.
Yeah.
So you can ignore those blue lines in the left-hand chart below the top one. That's just for the sake of visualization. That top one is the only one that matters. That's the one that I suspect points to your initial reservoir pressure. And it is, because the slope is required to be negative in the analysis, it does point to a pressure that's slightly above, based on the determination of that slope, is somewhere above all of the well flowing pressures that you've seen. Thank you.
Thank you.
So, excellent. We're going to round off this session with, one of my heroes, Carlos. Been very lucky to interact with him the last few years. I think, if I remember right, you were at Marathon before you started Hess, right?
Yeah.
And so he has a lot of friends in the audience. There's so many Marathon folks here, which is awesome. Sorry, I needed a little bit of time to pull up the presentation, but we should be in good shape. Right there, and then you have the arrows there. Warm welcome to Carlos.
I told Matthias didn't want me to present. They put me in the right before the lunch, right? So I put 2 or 3 slides only because I told you guys we were going to be anxious for lunch. So this is going to be quick, okay, and simple. So for many of you that been in the unconventional world for years, like me, I think you want to try to keep the thing simple, right? I learned that keeping the analysis in a simple way and looking for methods that can solve or find out a solution that can facilitate the analysis in a quick way is the holy grail, in my opinion. But if you want to complicate the analysis, you are free to do it, but at the risk of keeping in the Laplace space for the rest of your life, maybe. So this is on a slide that we all have to read carefully. Okay, no, I'm just joking. It's something that we've been asked to put here, so don't pay too much attention. So this is the agenda for today. Like I say, it's a simple method. We call it PUMPI. I'm going to show some examples of how are we doing it and how are we using whitCon to correct the method. Okay. I'll show us also some history cases and some final conclusions. So probably many of you, when you've been trying to plot PI versus time for many wells at the same time, you're trying to analyze a pilot or a path of wells at the same time, you got a beautiful plot where everything is confusing, right? So you don't understand really what well is performing versus one versus the other, right? Everything is noisy. So one way to denoise this is just to simply calculate the PI for every time step and sum of all of them and create some sort of cumulative PI. It's the same data where you're seeing from left to right, but it's the summatory or the sum of every PI for every time step for each well. And as you can see now, you're starting to see some difference performance from well to well, and that helps, right? That helps to say that, for example, the blue or green well is performing better than the red one, and so on, versus whatever we have on the left that is extremely noisy. It's just a simple thing, okay, that we've been using for many years so far. Probably you guys have been using that too. So in the same way, you can also do the plot versus cumulative order. Right? And as you can see, the same data you're seeing on the left, it's kind of converging. And when it's converging, it's telling us that perhaps the wells are not really performing different, but they are performing the same. It's just different pressure, right? The same energy for different volumes, but maybe different ways the wells have been operated. So it helps. At the same time, you can also plot versus cumulative total cumulative liquid. Some people have been doing that, and so on. So that's a very simplistic method. Now, what's the problem with CumPI? For many of you, or PI in general, apply for unconventional. By definition, the delta pressure that we put in the denominator is pressure, outer pressure minus bottom hole pressure. And I'm 100% sure that many of you have, like me, been using just one constant reservoir pressure per well or for the whole entire path. Same value. We all have been doing that for a while, and I'm sure that we're still doing it. But that's fundamentally wrong, right? We know that the reservoir pressure changes as soon as we produce, right? And also we have depletion. So close to the wells that are close to the parent well will not have the same average reservoir pressure as the ones that are in between some others or far from the parent wells. So the average reservoir pressure will be different. So what is the reservoir pressure then? How can we account for some reservoir pressure for every well? Well, simple. That's what my friend Matthias was showing up and telling me, you can history match the data and we can get some reservoir pressure profile for every well, right? And we can incorporate that dynamic reservoir pressure profile into the full PI. So rather than having just one value per well, one reservoir pressure value per well, you're going to have a dynamic reservoir pressure profile. Okay? Now your CumPI is going to look a lot better. So this is an example of the same data on the left, and it's looking very interesting on the right. The wells on the right have been corrected for other reservoir pressure after history matching the production using whitCon. So all of them have a particular average reservoir pressure profile that kind of close each other, right? They're not going to be considerably different unless you're completing the wells with different volumes and things like that. So you're going to have different SRVs or so, excuse me, or so on, then your average reservoir pressure is going to change. But things are getting more clear, right? So you're not going to have anymore that classical question, hey, but you're not accounting for depletion. Or the reservoir pressure that you were assuming was different from one well than the other, and so on. So this is a way to account for or sort out those kind of questions. Nice example here. This is actual data from pilot that actually Trey and I were doing, and I don't want to say what we were testing, but it was interesting that we all were saying that the pilot was overperforming the analog wells. That's what you're seeing in the left. And it was a great technology that we were applying. Everybody was happy. We were trying to sell this to our managers. So when I applied the method and calculated the average reservoir pressure using whitCon, what we have is what you're seeing on the right plot. So actually, the pilot was not overperforming the analog. They were the same. And then we were in trouble. But that's the idea. The idea is to use something that is consistent. The idea is something that satisfies the ego of the reference engineer, and at the same time satisfies our business and provides something that could be valuable for everybody. It's a simple method, like I say. First of all, we start denoising the data using the PUMPI approach or method. Then we use a numerical simulator to calculate the average reservoir pressure and correct the PUMPI. And apply this for any case for well performance analysis, either for single wells, a group of wells. You might argue that we should not address the PUMPI for a group of wells. Yeah, but that's something many people do. We just calculate one PI for a pack of wells. It's just a comparison thing. Doesn't mean that it's fundamentally right 100%, but it's one way to compare wells versus others. That's all I have, and I'm open for questions.
Thank you for a great presentation. To create a way to get the most out of data. I'm curious about your views on, you use PI typically for wait time, emissions, CSA state, and all that you mentioned, and have a good idea about the size of the reservoir. Have you encountered a situation that when the early time is dominated by the properties like pH,
Right.
that early time training effects are strong, but reservoir size that are small, they can potentially lead to higher QPI by the time it's improve well. I'm just speculating, the idea in my mind, before going out flying this thing, and the CFP can see as far as superiority on it can deceive you on the size of the reservoir. Thank you.
Yeah, I think it's a long question, but that's good. I didn't understand. I don't want me to repeat it. I think you were asking something like, correct me if I'm wrong there. What would be the, what will happen if we're in transient fluid and we're trying to, the effects of transient fluid on this kind of analysis, right? Is that what you mean, or?
More so, you know, the slope, you may have a higher PI, but it will decline faster. And it's not doing well, so you have a lower PI, but it takes forever, and then it means higher you are, in fact.
Right.
So, can you, if you analyze the
Yeah, I think you were, I mean, the question was more related on how can we use PI for a more consistent analysis versus other types of analysis. That's what we were trying to say, I think. Just keep in mind one thing, we're waiting until we reach BDF for this. So other than that, you won't have average reservoir pressure. Okay, so we are not in transient fluid anymore. Okay, and you'll be in transient at the early time, but the average reservoir pressure I'm calculating as after we reach BDF. Okay, so I don't know if that solved the question that you're asking, but it's at least making me feel comfortable about my reservoir pressure. I'm not changing my reservoir pressure and getting the reservoir pressure that corresponds to that particular SRD. And I agree with you that the PI tool sometimes be misleading if you don't do a right analysis. It's just a simple way to plot the data and compare wells versus other relatively short time. That's all. It's not extremely rigorous.
Can you explain what advantages you had over like comparing like LFT and OIP and contact volume and what else? Because you basically go through that to get to this point of what else is this giving you that those two comparisons have not?
Yeah. Yeah, he was asking me how can we compare this kind of analysis versus just comparing linear group parameters or so on and OIPs and things like that. I think it's the same. It's not that different. Just, we got, at least myself, we got those parameters, the linear group parameters and the SRV volumes, things like that. That's the way which we get, right? Other than that is, to me, it's just, you're just guessing. If you reach VDF and you get your linear flow parameter and your SRV, you can compare those. I always do that. One well versus other. But if you want to really plot the performance of the wells after you reach VDF, that's where these plots play a role.
Thank you. Excellent. Really good. Really good. Good discussions as well. Now we're going to go through a session that deals with something that a lot of people talk about, but I don't think there's really much consensus about how to deal with it when it comes to well interference. So if there's anywhere where we can try to help is to like, if there's standardized workflows, consensus in the industry, what's the best PHP correlation, those type of things, we would love to really help with some of that. So this session is the next session related to well interference. It's going to be one presentation by Leslie. It's going to be one by Donovan and also one by Stian. So for those that were part of the consortium the last year, one of the things we did there was to basically extend the multi-phase FMB method to be applied and to work essentially on a well group. So not only analyzing one well, and that's what Leslie's going to talk about now. So with that, Leslie, the stage is yours.
Okay, hi. So this work was started when just before we left, I left Cimerex. That is when it was being dissolved. And we were looking at, there were things that confounded us when we started doing FMB on the wells intersection. So for example, we knew that we produced clearance for a couple of years, then we came in the infill, and always slot one would be a terrible well. It would always look like it had a lower initial pressure. Then questions came up about, well, what should we use for the initial pressure for this well? And also we knew that, within the section, there was definitely interference between producing wells. So you shut one well in, you'd see another one, the production increase, and vice versa. You increase the production on one, and maybe you lose production on another. So then the question was, could we somehow look at, or should we be looking at this as a unit? So looking at all the wells as one unit, rather than trying to look at each well individually, or should we look at it both ways and see if we can get more information out of it? So that's kind of the background behind this. And I certainly didn't finish when I finished it when I left Cimerex, and then with SNAS, we could try and look at it again when I came here. So the way I decided to look at it was from a simulation point of view. I was trying to understand what's happening in slot one and so forth. So I set up a simple simulation where I looked at just one cluster going across an entire section, and in fact, just looking at half a section. So this diagram shows half of a section containing a parent well, or half a parent, which is at the left end. And then I have two wells that would be drilled in slot one and slot two after 2 years of the parent well producing. The slot one and slot two were gridded 4 fractures, but during the first 2 years, the slot 1 and slot 2 properties were actually matrix properties. So the parent was producing for 2 years from matrix everywhere. And then at 2 years, what I do is stop the simulation, change slot 1 and slot 2 properties to fracture properties, and then start back production under those conditions to see what would happen. The properties that I have here are typical properties that we thought we had in Permian. Fracture permeability is probably really high, but that's neither here nor there as far as this problem is concerned. The number I want you to look at is the initial pressure. The initial pressure for this entire section was 6,500 psi. So this is just a volatile oil. These are the basic properties that we use. Again, typical for some of the wells that we had in the Permian. Okay, so this is the first 2 years of production for the parent only. And the rates are multiplied by 100 to make them look reasonable. So nothing really special on the rate field. But if you look on the right-hand side, what I have is a plot of the mass density with distance from one edge to the other. And it's you can see that on the bottom of this plot, let's see if I can get this pointer. Okay, on the bottom, do you guys see a pointer? No, you don't. How do you get the pointer on this thing? Oh, cool. So if you look at the bottom of this picture here, I have where the half parent slot 1, slot 2 positions are, and you can see that most of the depletion is in blue. So as you expect, the area that the parent is draining is most depleted. But you can also see that well into where slot 1 would be eventually, there's quite a bit of this depletion as well. And you can see that even better if I zoom in on the slot 1 area only. So I'm just looking now along the fracture plane, what would be the fracture plane in slot 1, just to see how pressure and saturations would change before you do anything. So at the end of 2 years. And you can see the pressure changes in slot 1 from an initial pressure of about 6,000 psi far away from the parent, down to as low as 1,500 psi right next to the parent. So there's a significant pressure drop within the slot 1 area before you even do anything, before you even open that well. You can also see that if you look at the saturation profiles, you are undersaturated for part of that slot 1, but then you're saturated at another part. The average pressure within the slot 1 region is 4,700. So it's quite depleted compared to the initial pressure of 6,500 psi. So it's no wonder that when you open this well and you estimate the initial pressure, it's going to be a heck of a lot lower than you expected it to be. Okay, so in order to do things consistently, what I did I went back and I tried to do FMB analysis on the parent, and then I'm going to do on the infills as well. And to do everything consistently, I'm going to assume that everything's starting at the same initial pressure of 6,500 psi. They all started from the same tank, so it kind of makes sense to me that we should treat them as they came from the same tank, even though it's obvious that slot 1 will not have the same apparent initial pressure. This is the FMB plot on the parent only for the first 2 years. And, we got a pore volume that was slightly bigger than you would expect just based on the fracture half-length, so based on its SRD. So it's about, if you look here, it's about 106% of what you would expect if it drained only its SRD. Now, as I said, after the 2 years, we open all the wells. So we open all the infill wells. So there's a new now, these infill wells are producing at the black pressure profile that I showed here in the plot. Of course, you get this big jump in production from the infill wells. The parent well actually drops in production for a while, then it comes back. And at the end of a further 2 years or 1,500 days, this is what the depletion looks like in the reservoir. It's much more uniform. the parent area is still much more depleted than the infill area as well. If you go and look at the entire period, the entire 1500 days, put it back into the FMB plot, that's kind of shown the extra data that I have after the 2 years is shown in the yellow. And now what you get is that the parent volume has actually increased a little bit. It was 106% of its SRV before. Now it's about 111%. Of course, it's not seeing the entire pore volume. The entire pore volume in this case is 13,042 million, thousand barrels. But if you go ahead and analyze each of the infill wells, then slot 1 and slot 2, you see that slot 1 is only showing as 81% of its SRV, so a lot lower than you'd expect. And slot 2 is showing about what you would expect from its SRV, so 98.5% of its SRV. And so if you add up all of these, the actual pore volume is about 13 million. And if you add all of them, you get about 12.3 million. So you get about 95% of the, and you add all the analysis, you get about 95% of the actual pore volume that's being drained. Okay, so now that's if you do the analyses separately. What about, could you somehow combine all these things into one and get one super well and see if you could handle that? So it turns out it's pretty easy. I mean, to combine the rates, all you have to do is add them. Okay, that's not a big deal. But the problem is, how do you combine the wellbore pressures? And I guess you could do that for a single phase flow. So if you had three, and I've never actually done it. Okay, if you had 3 single phase tanks all producing single phase flow, starting from the same pressure but at different bottom hole pressures, could you combine them into one pseudo tank? And my intuition said, well, you probably could, but it would probably be based, the wellbore pressures would probably be based on the pore volumes that are being drained. I don't know if that's true, that's just intuition. But if I were to try to do that with this problem, what it would mean is that at any particular time, I should combine the bottom hole pressures based on the instantaneous volume that each one drains. In other words, the inverse of the FMB slope. When I thought about that, I said, there's no way this is going to work. So this is not practical because the FMB slope, the FMB points are noisy. That's just the nature of things. If you try to take slopes of noise, you get a hell of a lot more noise. So you can get anything you want, it's a waste of time, completely impractical. And so I decided to try something completely heuristic and decided to combine the wellbore pressures based on the fraction of the total mass each well produced. Again, it's completely intuitive. Just tried it just to see what would happen. And so on the left-hand side of this plot, you have what the actual production of the wells are and their actual bottom hole pressures. And then on the right-hand side is a pseudo-well that you create by weighting the pressures, like I said. And you can see that at early times, what happens, well, at early times after the 2 years, when all the wells come on, the parent well pressure influences the pseudo-well pressure a lot. But then as those infill wells come in and they add a lot more to the cumulative production, they start influencing it as well, a lot. So now if you look at this pseudo-well, so now I'm treating all the wells together. The plot at the top is the parent well by itself. Obviously, it was producing by itself for 2 years, so it's the same plot I showed before. And then when you add all the wells together, you get this new line up underneath here. And that shows a pore volume of about 93 or 92.5% of the total pore volume. So if I added all the wells together, I got 95% of the total pore volume. If I did this method, I get about 92% of the total pore volume. So that looked fairly promising. And so I applied this to a bunch of different, maybe 5 different simulation cases, different fluids. So it's by no means an exhaustive study, but on all the cases that I ran, it seemed to work. So I said, okay, cool. Let me ask my friends at Coursera, can I try this on some real data? And they let me work on one section containing, I think it was 8 wells. So the top left-hand plot is for the parent well. And that parent well produced, I can't remember, maybe a couple of years by itself. And then they went and they drilled all the infill wells. And so there's a lot of noise in this parent well. Okay, the actual first 2 years is somewhere down here in this bottom left-hand corner. But eventually, you know, a bunch of stuff happened. You did the fracts, you got interference. It looked like the pore volume increased for a while and then settled down and it came to a final line. Then if you look at all the infill wells, a couple of pages of that, so this and this, you could get estimates of the pore volumes of each of these infill wells. Again, if you combine them all into one pseudo-well, this is what you get. So again, the yellow line is for what the parent was by itself before, and then this guy is for all the wells together. If you compare those, then if you sum the FMBs for all the wells, the parent and its infills, you get about 151 million. But if you look at the pseudo-well, again, you get about 155 million. Okay, so they look fairly similar. But in my mind, what the advantage of doing this is, well, first of all, I don't think you will get more information by combining the wells than you do from adding the wells together. But what you do get is you get a lot of smoothing out of this noise or of the interference. So if you look at the parent well, it's a mess, okay? If you were trying to analyze this thing week by week, you're in a lot of trouble because the line is going all over the place. Whereas if you combine them, you somehow get, you know, all of the rates sort of cancel out, and the pressures get nice and smooth, and you get something that is much more palatable. And this thing, which I think makes quite a bit more sense. So, you know, I wish I could tell you that this was perfect, and you know, I felt confident that it's all correct. As I said, to me, it's kind of preliminary. There's a lot of things that I still would like to answer. But anyway, what I found so far is that the pseudo-well gives comparable results to adding the wells together. It cancels out variations in individual wells. There are problems. I honestly would like to figure out how to do this on a web. You have different initial conditions, different initial fluid properties, etc. Now, I know that this has been put into, by the way, you know, I said a little bit earlier about slot 1 and what you should use for the initial pressure. So we did some tests on that, and this is not going to be the presentation. But what we found, and yes, 3 or 4 of us at Cimerex at the time, including Narayan, who was there, we found that you should be using what the initial pressure for the section is. Don't try to use what the slot 1 is. If you look back to the slide that I showed on slot 1, yeah, the initial pressure is completely lower, but then the initial saturations and everything are also different. So what do you use then for the initial saturation? What do you use for initial PDT properties? You know what it is initially, at least you have more confidence in that at the initial section values, but you really do not know what it is for the slot 1. You're playing with fire by doing that. So anyway, as I said, I know Witzner's implemented this. Maybe some of you guys have tried it. I'd really like to hear some feedback. I no longer work with real well, so I'm in the dark. But I'd like to hear what you guys think, if anything. Thanks.
You are not going to one question today. You promised me any question.
Yep, that's good. If you had any hard questions, I'd tell you to call Barry. He's not here.
One more round of applause for everybody. Thank you.
We're good. So we're going to stay in the well interference lane, a little bit more on the well testing side of things. So as I mentioned earlier, we introduced our first version of child pressure group earlier this year. A lot of iterations on that, allowing for different types of derivatives per day, weighted central difference, all kinds of graphical things. We're still working on a bunch of interesting things. Feel I'm getting in new suggestions on how we can improve that feature every single week. Donovan's done a lot of good work on and trying to answer some questions that I think is relevant for everyone, and that honestly we don't have any best practices on. So he'll share some of his findings, and hopefully some of you have done similar work. So it'd be great to open some discussion there, and hopefully we can create some kind of consensus. So with that, Donovan, stage is yours.
All right. Good afternoon, everyone. My name is Donovan Armistead, and I'm a reservoir engineer with Devon Energy. So a couple of months ago, Matthias sent me an email, and it read, an invitation to be present. And I read it as an invitation to attend whitCon, which I thought was a great opportunity, and I thought if I had time, I'd gladly attend. And at the same time, I was also neck deep in the CPG analysis. This was my first one, and admittedly, I was a skeptic of the interference test. And I was skeptical for a lot of the same reasons other engineers are. For one, how are we actually using this data to help inform future decisions? From a subsurface standpoint, what does this really mean exactly? And lastly, if we ask a bunch of engineers to do this across the same basin, how can we maintain that they're actually doing a consistent analysis across the board so that we can trust the results? And in an effort to essentially convince myself that I can make use of the data that we had already collected, I did a bunch of sensitivities on some of the variables that go into the analysis itself. And Matthias was curious, so I shared some of my work with him. And he replied, Donovan, this is great work. Maybe it's something you should show at whitCon, and he even tagged it with the wiki face. And I remember sitting back and reading his response, and I was like, oh crap, we went from 0 to 60 here real quick. And I went back to that initial email, I reread it, and it was actually an invitation to present, not an invitation to be present. So here I am, and I promise you guys I can read, but my goal today is to share with you guys some of the work that I worked on for the CPG test. So I've already talked about the importance of consistency in the test itself, and depending on how you approach the analysis, you can get a wide range of variables or answers depending on how you approach it. And in this plot, it does a pretty good job of illustrating what I'm talking about. What we're looking at here on the y-axis is the MPI, and then on the x-axis, we're looking at the derivative window. And the MPI is just the magnitude of pressure interference. That's our way of essentially trying to quantify what the interference actually looks like, put a number to it, so to speak. And the derivative window is just what we use when we're trying to smooth out the derivative itself. And I'll get into that a little bit more later in the presentation. But what I've done is I've done a sensitivity on the MPI by adjusting the derivative window to kind of see how it's impacting the overall answers from the test. And what you'll see is that as you increase that derivative window, you start to get a really different MPI. It starts to fall off. And so if you asked a bunch of engineers to do this and they did a range of derivative windows, you'd get an answer that ranged anywhere between 0.5 to 0.25. So you're pretty much saying, hey, I have a pretty decent amount of interference, or, the interference is pretty moderate, probably something that we're all right with. And so that's where I'm kind of, I think it's really important to be consistent here, and that's really what spurred this whole study. Now, before I get into any of the details, I think it's important to talk about the CPG workflow itself, just because if anybody's not familiar with it, they'll probably be pretty lost here. The whole thought process behind the CPG test itself is that you want to get a really good initial pressure trend. And at Devon, we do a lot of this post-frac, and so what we're doing is we're getting a trend off of the leak off. And then as we open the wells, we'll see a deviation of that leak off, and that's your interference. Now, you can also do this on wells that are already producing. So wells, you can actually shut in and get a buildup trend. You can also trend that, and as you open wells, you'll see a deviation in that regard as well. And so if we look at the steps at a high level, what a lot of people will do is they'll condition the data, they'll fit the initial pressure trend, as you can see with this yellow line right here in Whitson. You'll select your time that you've popped your offset well. And then you'll calculate your delta P and your delta P prime, and then from there you can calculate your CPG and get your NPI. Now there's a lot of variables that go into this. How are you going to condition that data? Are you using some sort of a weighted average, or are you using an agile smoothing function? How am I fitting this initial pressure trend here? I can have some softwares will do it automatically based on how I choose 2 points, and Whitson you can kind of manhandle the data and fit it however you want to. What am I using for my derivative function? Am I using the Bourdais or the central difference method? What is the frequency of my data? Is a big one. Am I going from 1 hour to 1 minute? What is the derivative window that I'm using, which I spoke about in the previous slide? And then am I looking at a pressure integral versus just a normal derivative? So what I did was a bunch of different sensitivities on 2 separate wells and a single interference test. I used the 2 separate derivative functions here. I used the central difference method and the Bourdais. And then I used a range of different data frequencies from 1 minute, 5 minutes, 10 minutes, all the way up to an hour. After that, I used a bunch of different derivative windows. And I went from 0.01, 0.1, 0.2, all the way up to 2, which is, in some people's mind, probably pretty egregious, but I figured if I was going to do it, I'd go all the way. And then I did all this in Whitson Plus, and I conditioned the data using an agile smoothing function in Seek. Now, before I even got started, I looked at just pressure versus time data. I feel like this is a really good common sense check on the analysis itself. So what we're looking at here is the pink well was just put on production, and in Seek, it's just a software that Devin has where we can look at time series data. I was able to kind of zero out all the pressure to just the point where we popped this well. And it provides a really clean look at what the pressure is doing before and then what the pressure is doing after that well was put online. So if you look at this orange and purple well here, you can see that we have the same leak-off trend essentially. And then after that well was popped, the orange well shows more interaction than the purple well. So directionally, what this is really telling us is the NPI that I choose should be higher for that orange well than the purple well. Now I talk a lot about derivative windows in this presentation. And for context, I stole some of the information from the Whitson user manual, and I kind of modified it to make it fit for purpose here. But to explain what the derivative window is, in terms of the Bourdais, it just provides a method for you to smooth that derivative based on the log cycle window sizes. If we look at this plot here on the right, the star is a point at which the derivative is calculated. And then the squares here on either side of that star are the points that are used in the derivative calculation. L1 here is just one derivative window, essentially what you're using to calculate the derivative. And then L2 is a larger window size. And so the larger window sizes will provide more smoothing for the derivative itself. Another point here is that if I were to move this star to where this square is, I'll actually start to truncate the data because the point at which I start to use to calculate the derivative and using the calculation would actually extend beyond the data that I have. And so the wider that window, the more you'll start to truncate that data. You can see that here on the next slide. So this plot is just your CPG versus time. And this blue line right here is, each one of these lines actually represents a different derivative window. This blue line is 0.1, the yellow is 0.5, and then as you come down, you're actually increasing in your window size. And so what we can see is that when I increase my window size, the first thing is I am truncating my data pretty significantly whenever I get up to 2. The next thing you'll probably realize is that the NPI value or the CPG itself is actually coming down. And so depending on the window size, your NPI can vary between 0.75 to 0.5. Next thing I looked at was the derivative versus the pressure integral. And the red line here is just the pressure integral, while the blue line is the actual pressure derivative. And if you were to ask a bunch of engineers to go and use the derivative and pick your NPI versus the pressure integral, you'd probably get a lot more consistent results picking your NPI off the derivative itself, because it's really this clean straight line. And you would probably get more inconsistency choosing it off of the blue pressure derivative itself. So this next slide really kind of ties it all together. What we're looking at here is very similar to that first slide that I had. And we're showing the MPIs here on the y-axis, and then we have the derivative window here on the x-axis. And we have two separate wells, and each one of these lines for each of these wells, the different colors, is a different frequency of data. So the question here is there a sweet spot with the derivative window and the frequency of data that would give you a pretty consistent MPI? And if we look at this, the first thing you'll notice is the blue line, which is your 1 hour data, is actually being truncated. And so this is the same thing that we just talked about with the actual Bordet derivative. If you have less data and you increase that window size, you're going to essentially truncate that data a little bit more. The next thing you'll probably see is that this red line, which is your 1 minute data, is probably going to provide a higher MPI pick on well 2, while it's going to give you a lower MPI pick on well 1. And I had to sit back and think about that. Some of that could be human error, because I'm the one that's going in there and picking everything. But that is your 1 minute data. And so my thoughts are, if you have really high resolution data, sometimes the noise in the gauge can actually impact the interference that you're seeing. And so if you're trying to go in there and figure out the magnitude of that pressure interference, sometimes it can get hidden in the gauge noise itself. And one thing I also noticed was that as the magnitude of that pressure interference gets less, your capacity for error gets a little bit larger for the same reason. And if we look at the pink and the yellow lines on this plot, they track pretty well together. This is my 5 and 10 minute data. And the fall off from that MPI, at least on well 1, isn't as considerable as some of the other resolutions. And so here I decided that for my analysis, sticking between 5 to 10 minutes resolution was the most consistent way to approach the analysis. And the last thing is, if we look at the early time results across the board, the MPI is pretty consistent until we extend beyond a 0.6 derivative window. And so my recommendation here, and one thing that I kind of held constant in my analysis, was that I stuck between a 0.01 to a 0.6 on the derivative window. This last slide is just a slide of your delta P's. This is another good QC to make sure that the results you're getting from the test actually make sense. What we're seeing here are 4 separate wells stacked on top of each other, and we have the delta P's being plotted. And ideally, if you have a higher delta P, you should have a higher MPI as well. And so these red numbers are the MPIs that are calculated in this test, and you can see that the delta P's do track pretty well with those MPIs. So my go forward approach here was to analyze off the pressure integral, use the Bordet. Use of the Bordet or the central difference method really didn't matter as long as you're consistent throughout the whole approach. And then use data that has a frequency between 5 to 10 minutes. The derivative window, keeping that between 0.2 to 0.6 really drove consistency. And then QCing that MPI against really just common sense checks with your delta P and giving your pressure versus time data was pretty useful. If anybody's curious, we actually did use this data to inform a decision. Gave us some interesting insight into how frac order impacts frac geometry. And it also gave us insight into what we think the flow unit might be for a spacing test. That's all I got.
It depends on, you talk about pressure intervals where, kind of basically, but probably we were talking about earlier, is the QDI thing, and that's just reduced noise. It's exactly the same thing. That's why we use our intervals and kind of RPA as well. In the same equations, and while grading NI and a vertical paper when you know students to get an LC in their project. But it's also the same reason to reduce noise. And better because reduces noise that also reduces the signal, and these others are that's why we use derivatives, which amplifies the signal but also amplifies the noise. Any questions?
Thank you, John. Today, actually, my question is for the PhD candidate. I haven't personally dabbled in the whitCon for the CPC, but I know these other kind of well-known software or derivatives which is actually like organic itself, right? So I wonder how there's this, I think you going there, the smoothing function that was originally published. How does this compare to that? Like if you have to use the same analysis, getting a derivative and the smoothing, and over smoothing can result in different PPT reading and all that. You have to try to
Yeah, absolutely.
the derivative integral, so you call.
Or logs, yeah.
Yeah. Well, how does it compare? Yeah. So can you just repeat the question?
Yeah. So the question was compared to, I guess, Bourdais' original calculations in his original tool. How does the calculations in that compare to the calculations happening in Whitson?
Yeah. So who knows the word Bourdais here? Who knows the guy? I'm talking about whether someone that we like where the word. He was on the top of the tackle. Yeah, that's what I did. And people told me to want to work the risk, but also the fact that they wanted to manage the risk and the default in Kappa on the risk estimating is good one too. I think it's anything else that maybe or something like that as well. We actually did the same thing, and we actually got the data code from Ben on that Chevron, and we were using exactly the same thing. That was exactly the same thing that they had involved. That's what we do.
More than a question, I guess, is a comment. I understand your motivation to look at the smoothing factor. That's what we call it in the old time. And it's still being the same for TD analysis. That's a dangerous tool, right? So the nicer the derivative, the more confusing. So you never use less than 1.1, 1.2 or so. I mean, increasing that value will make the derivative look nicer, but at the same time more dangerous. Right?
Absolutely.
In frequency, I never use less than 1 minute. Or sorry, more than 1 minute. 30 seconds is my preference. 1 minute is okay.
Okay. Yeah, no, that's great.
And just to add on, I think, I've never dabbled in this until last year, but I think it's been a lot of success in 30 seconds up to maybe 15 minutes. But if you have less spacing within a data point, the degree of smoothing requires less as well. Those things will come into play. Go ahead.
Thank you very much for this great presentation. I enjoyed it. Just as a thought again, and a question, have you tried doing that sensitivity by looking at the flow regime so that we can again how it's moving or how the moving factor will affect these things? I'm saying that because I read that in the hard way. I did a test with the moving factor. So just wanted your thoughts if you have compared the linear to the flow regime against the moving factor.
I've not looked at that. Yeah, so the question is, if I'm understanding right, have I looked at this in context of the flow regimes against all the wells? Is that right? The answer is no. I have not. But that'd be pretty interesting. So are you thinking like in the sense of maybe like an RPI plot as you're looking at it? Yes. Yep. Okay. So like after it's already hit a boundary, how does the derivative or the smoothing factor hit that versus transient? Yeah, that'd be interesting. I have not looked at that. Might have to though.
Sorry about myself, but you tell the test, you said? Or like a blanket? And that's something perfect. We'll skip the pretty great question and the further presentation from Donovan. I think it's super relevant. It's always fun to see how people get passionate about CPG. Well, in the future, when we launch this, most people will either have like a day off there, like how do you get anything like it? And Donovan, it's only question in time. So it's really amazing. But thanks again, Bob.
So as you guys can imagine, when we were setting this program together, we try to kind of keep it, kind of combination of new things and the kind of more FYIs of things that we've implemented in the software on your request. So that's also why we're keeping it this kind of combination of new research or new best practices and things like this, which is the next presentation with my very good colleague, Stian Midland. I just call him Dr. Midland. So I want you to try to adopt the same thing. But it's actually been a super big year for Stian, so if you meet him later, make sure to congratulate him. Last year, he actually presented at whitCon as well, but since then, he's both gotten married and he's gotten his PhD. So now we actually can call him a doctor with some confidence. So with that, with that, Stian, the podium is yours.
Thank you, Matthias. Good afternoon, everyone. So one of the new things that we released with this in whitCon+ this week is, as Matthias mentioned earlier today, multi-well numerical modeling, sort of expanding our numerical model from only having single numerical models to a single well numerical models, now also supporting multi-well numerical models. Yeah, I'll skip that slide since Matthias sort of laid out my entire life there in the introduction. But yeah, so I'm one of the senior and software engineers. I work mainly on developing and maintaining the RS and BGP calculation engines. So before we go to the multi-well, I just want to try to build this up in a little bit like how this has been developed. And obviously, the single well numerical model, that way of modeling multi-fractured hydraulic horizontal wells, is probably what most of you are familiar with. You make assumptions about symmetry, and you model this small part of the reservoir in this box shown here, and that is sort of the well box, we call it. And whitCon+ has a couple of two features in reality that are using this type of numerical modeling, where you can sort of just change and vary the parameters of this. So the model itself is fixed, but you can sort of change its size and permeability of processing distance. So I'll try to explain this in terms of numerical model, call it complexity, going up the stairs of complexity. You can sort of think of it in the same way as a sort of the usage. So like most of us are using numerical modeling and reservoir simulation are likely on the first and second step. That's yeah, except for Matthias, he's in the basement somewhere doing LinkedIn. Yeah, the most of us are. So numerical RTA is sort of the most constrained variation we have of single well modeling. There we are assuming that both the fracture half lengths and the fracture height and the reservoir heights, they're equal, fracture the extent and the half length, and we're resolving that fracture half length and permeability in the numerical RTA feature. That was put in last year. Second step, singular numerical model. This is actually where you can say whitCon, what used to be whitCon PVT. Probably not many of you know this, but the very first version of whitCon+ was called whitCon PVT. And then we added numerical modeling and this capability. I liked it with this capability here, and it became whitCon+. And this is essentially there's a single petrophysical layer. You can then vary. You can decide if you want to penetrate the fracture completely or the layer completely with the fracture, and you can also decide whether you want to have volume beyond the fracture tip, but that was the limitations. But since then, things have changed. There's been added many new things, new features, new ways of adding incremental complexity to the model. I'm just going to mention what's new with this release. I think it was Bruce who asked us a while back if we could add So we had the half-bounded option that you could lock in one side and then have like a half-bounded well, but now we've added the capability of having asymmetric lengths and fracture half-lengths on both sides. Another sort of incremental complexity add-on is for those of you who are using multi-layer single-wall models, we can now do varying fracture half-length with depth in a different petrophysical layer. But at the top of the widths and numerical complexities there, we have the multi-well numerical model feature, just released now. And what differs there is that the well box is the same, but now there's more wells in it, several end wells. We still make an assumption about symmetry and lock in the model in a tip-to-tip fashion. We draw a box around one of the fractures, and from a numerical model, the model can be described like this in the gun barrel view, sometimes called a wine rack view. It's a vertical. You can place the wells in different layers, different petrophysical layers, and you can also choose how the fractures are, how long they are, the XF, and also the height, which layers they perforate, etc. And the wells can also interfere with each other, giving the possibility of getting more well interference in the numerical model. Sorry. So the numerical model canvas looks like this, very similar to the single-well numerical model. You'll find it here under multi-well analyses. The way we would just initialize the model is starting out by specifying the reservoir data. There you can define a number of layers, the petrophysical properties of each layer, the thickness, and so on. Once the layering is set, you can, of all the wells you have in the project, you can decide to bring in different wells that, physically are neighbors somewhere. If you're modeling a pad or a drilling spacing unit or something, then you can place these wells in the different layers, apply the fracture half lengths and distances between the wells, and to decide which layers you want to perforate with the hydraulic fracture. And as the fluid, you can decide to have the same fluid in the entire model, or you can have a layered fluid system, different fluids in different layers, and you would set that. And then the final thing is to decide what kind of control you want to set for the well. And the final results will look like this. It will present a series of plots, all the same plots as in single-well numerical model. One for the total, so the sum of all the wells that are included in this model, and a pane or a tab for one of the wells individually. As Matthias said, the feature is it's new, it's in the making. I want to bring a shout out to my colleague, Elina Yusra. She's not here today, but she's one of the senior PEs. And she has been spearheading the development of this and is fully dedicated to continuing developing and maintaining that feature going forward. So those of you who will use this feature will hopefully get to interact with her. And with that, I'll say that's it. Thank you.
Just a couple of notes here. So the groups were actually out when we name dropped in there. So we went to one of the requests. Very similar requested by a lot of other people as well to have more flexibility on the factors being asymmetric, particularly for like a edge wall, etc. The second thing there was fracture half-life in the different layers. That's as simple as technical to do that was presented on earlier, to work on Pseudo-well and do that. So you create those models. You take the area units then, and you recognize and stuff, so you just distributed the area to another geometry, and you actually get really, really similar. That's very effective way of making that. On the multi-well, I know a lot of you guys have been in there already, seeing and interacting with you on that, only in a couple of days, but I'm sure it will be going to the very cool things to get involved. I think, we have been thinking a lot about the people that this model of stage so we can have this, transporting the whole parent completion of the different types of applications, which is newer ones. Now we're kind of keeping the same, the assumptions that are the same in terms of orchestration, just a lot of the same development model. There's a lot of people these models and, take less than a minute. That's just a couple of add-ons there. Any questions? And no. You're just getting the microphone next time. The game costs $150 to rent if you get there. They've got an own process over there. You have no turn. Two questions though. Are we guys planning to release the function that we are symmetric spacing between vectors? Yeah, like the spacing between the vectors. Yeah, so in the first version, that's exactly what I mentioned now with the stage, the stage. You can have different back spacing between each back, or you're able to you can have different cross spacing between the current balls that we have in.
I think Lester has a question.
Can you bring around and exist at different times?
Yeah.
So you can do like what I did for these 2 years, all around and actually work with them.
Yeah, so you would have to add all the wells into the model initially, but you can, based on the timestamp of when the well starts to produce, that will be honored in the numerical model. So they can start to produce at different points in time.
So you're putting those periods and those wells that are not producing to be fixed before you start.
Yes.
So that's a good position on the time. There was also a question here related to basically the price shows is variable Pakistan JV, which is 1%. Yeah, and I was actually discussing here the probability of taxes that comes. We were actually wondering why it goes like up in the beginning and then down at the end. Yeah. So, I think the time and questions that are a lot around. I had a question on, I guess, more like the office space, recovery, or enhanced recovery, your company, but reactor water. That's on that stuff. I think on just gas, I can answer that real quick. We only have a black oil somewhere right now, so we'll probably wait till we probably have a conventional somewhere to be much some gas in the numerical piece. But I know water and electricity, black oil, water, electricity, overall is coming very soon and on the backlog there. It's been impressed about a lot of companies on that front. So maybe that's the second thing we can do that for this. On the gas and water side, though, there's a lot of exclusive calculations and then fees that make in first contract underneath that you can calculate. You can do the gas on top there, PCT experiments. So there's a lot of flexibility there that you can do. But that's just an empirical situation as well. This is the time now, John. I think we need to continue. But thanks again for taking part.
So we're actually entering kind of the last standard session today. We're going to go through this session. It's going to be a pure RTA session. Then it's a PM break. And then we're going to come back, and then it's going to be these, it's not a competition actually, but it's like a comparison of different, 3 different interpreters going to interpret the same data set. We need to talk more about that later, but it's going to be fun. But it's not a competition, it's more of a discussion. And that data set will also be available for you guys if you want to test and do the workflow yourself on those wells. What do you think kind of makes the most sense? And there's no really good answer there. This session is related again to RTA, and what all these guys have in common is that they've done RTA or FMB on hundreds and hundreds of wells in Whitson Plus before, or just in general, really. And the first one to present is Brian Collins, and he's going to present on the main assets that they're developing. Is the Anadarko Basin asset. So with that, Brian, I'll just leave the podium to you.
All right. Hi, Brian Collins. I work at 89 Energy, which is a very small oil and gas company, about 25 people or so. I don't think it's out of place to ask a room full of probably what I could safely call nerds. If anyone likes science fiction, can I get a show of hands? All right, so being at a small company, I sometimes worry that I'm similar to these science fiction stories where you have a small group of humanity that gets lost in the stars for 10,000 years. And by the time they're found, they've deviated from the genome, maybe grown fins or a third eyeball or something like that. I get a little worried that when I do a presentation, I'm the lost splinter of humanity here coming back. So anyway, I'll move forward. All right, so 89's assets are in Oklahoma in the SCOOP. We have assets in the north, central, and south part of SCOOP, but I want to focus today on our southern part because it is by far the most complicated. And the reason I say it's complicated is because it's generally characterized by a lot of structure. It's also got a lot of vertical well production throughout the area, and so by some combination of those two things, you end up having a very strange looking phase window map, where up on the top of the structure, you have a lot of dry gas. You move down through our position, which you can see is kind of there with the blue boxes, and you start getting increased liquids content until you get into the basin proper, where a lot of Marathon, Oventive, Continental have done their work, and you start acting much more normally as far as unconventional resources are concerned. On our acreage, it's very normal to see wells that start out in the 1,000 to 2,000 standard cubic foot per barrel GOR range, but then ultimately end up producing about 10 to 15 BCF or sometimes even more. And those kinds of final gas recoveries make it very difficult to handle in a single fluid type model in Whitson. With all these complicating factors, though, it is still very important to understand what's actually happening in the reservoir, I believe, and not just using correlations from nearby wells to sort of guess at what your appropriate recoveries are going to be in your unit. So I'm going to walk through a workflow that I've kind of developed, a little bit of a modified workflow as far as Whitson is concerned. It doesn't just follow the normal steps that you would take. The first thing I'm going to do is just go back to good old decline curve analysis, where I'll just look at what I think a decent estimate of the EURs are. From there, I'll do some floor material balance and see how that compares to the decline curve analysis. After that, I'll move into some single phase RTA models and the numerical models, and then finally get into a dual layer model, kind of like what we just talked about. In fact, I was preparing this presentation the other day, and I, from one morning to the next, saw where I could now change the half lengths to everything. So I was like, well, it's a little late for this presentation. And then after those, using the highest confidence estimate of contacted pore volume that I can get, I'll fit what I've learned into a basic volumetric model, so use some observations from some appropriate analog sets, and then see how many wells the volumetric model indicates that I can fit into my unit. All right, so as a bit more introduction to the area and the difficulty that the fluid behavior creates, I'd like to review the basic stats of the case study well here, the strike well in southeast portion of the acreage that I just showed. The 7,700 foot lateral, the initial GOR was about 1,700 standard cubic foot per barrel, and it's classified as a volatile oil per the Whitson equation of state. But notice that today the GOR is over 70,000 and it's still climbing. In general, I have found it very difficult to reach that kind of GOR with this kind of fluid type of volatile oil, even with severe adjustments to the relative permeabilities, and we'll get to more on that in a little bit. So I like to use the newer fractional RTA functionality in Whitson to give me some insight into B factors. And we can see that for oil here, you've got a 0.64, which seems very reasonable. But on gas, we're in the range of 1.6 to 2.9, which is pretty high. Although I do think that that's the first signal to me that I'm looking at a more complicated system where I've got some sort. I mean, this is to only be at 2.9 for this well is actually fairly low. I have some that come in from fractional RTA in the 5, 6, 7 range. So yeah, it just tells me that I've got something a little more complicated than a normal system going on. I'm not accustomed to putting 2.9 B factors on wells when I forecast them, so we're just going to say that a low side gas EUR here is probably about 14.5 BCF. All right, as I mentioned, the next step here is going to be to move into flowing material balance. It seems to do a fair job of getting me in the ballpark for both oil and gas. You can see in the table down below that I'm about 6% off on oil and a little more on gas, not quite producing enough. That's going back again to that initial PVT type that I'm using. But the big giveaway to me that I'm probably not looking at realistic numbers are the recovery factors. And I don't know if you can see those from where you're sitting, but they're about 4% on oil and about 95% on gas. And I've done a lot of flowing material balance throughout the entire area. And I'm used to seeing something more along the lines of probably 12 for oil and probably somewhere anywhere from 55 to 75, maybe even 80 on gas. So then, as I mentioned, the next step is going to be to move into a single phase numerical RTA. Using that, I've been able, and by constraining fracture conductivity, I start to replicate the cumulative oil curve, which is kind of always the first thing that I go after. I don't actually have a very good lock here on GOR. It kind of gets in the same place eventually that the curve or that the plot would show, but it's not really honoring the shape of the curve there. And then you can see right when I put that into the numerical model that the result is not anywhere close to what we'd expect, especially with respect to the GOR. What I get over and over again using these low initial GORs to use in the numerical model is this sort of breakover pattern here in the GOR. And again, I mentioned here that this is even with a pretty low rel perm for gas and a pretty high rel perm exponent for oil, and that's never going to touch what I've got going on here. So the next step for me is always to just play around with the GOR a little bit. We get something that gets us to a pretty close match on the oil cume curve and the gas cume curve, but again, we're going to end up plateauing out on GOR. So not something that I want to move forward with here. So I'll take a step back on that, and instead of increasing my GOR to try to match both phases at the same time, I'll go ahead and decrease the GOR to around 1,000. You can see it there, it's 950, and see what happens. And the other thing I do here, which I was trying to think if there was a way to plug it more and talk about it more, is I've increased now my fracture conductivity to 100, which actually for me is essentially infinite. I work a lot of wells in the Woodford, and they're just over and over and over again characterized by low fracture conductivity. I think I need to talk to the guy that presented earlier on the fracture conductivity about that. But anyway, what was I going to say? So at 100, it's pretty much infinite for me, and I get a really nice shape on the oil curve here and on the Bowie plot. Moving that into the numerical simulator, instantly got a nice match on oil cume curve, and as expected, obviously very far off on gas. So now is when I move into the two-layer model, and I hope you guys can see the box there. It's a little small, but what I wanted to point out was just how large I had to make the box on gas. I think it says about 240, if I'm not mistaken, feet, and then also had to really drop the permeability down to sub-nanodarcy levels in order to, again, I went back and I should have put the cume curve on here. It does honor the shape of the cume curve very nicely, but I can't show that right now. So the two-layer model helps to give me a lot more confidence that I am in the ballpark on total contacted pore volume, and I can move on to my next step. All right, so as mentioned initially, the point of all this is to have a greater confidence in my ability to estimate reservoir volumetrics, and then ultimately to get mass balance with the inclusion of some child wells. We're going to look at things like spacing and also what the type curve should end up being. So there are a few overdeveloped units in the area, that I think if they had taken this approach of a volumetric model like this, would have been far more successful rather. They ended up drilling far too many wells and paid for it. As in the image below, the little cartoon down there, we need to estimate what's been contacted by the parent well, and then what we need to have an estimate of what the child wells are going to be capable of and what they will ultimately contact inside of that volume. What makes that a bit tricky is that the nearby full development units are really located in a different pressure and fluid type regime, and that's because of these faults that are right here in this map. So we can't really use these OBO units. Notice though, however, that they are drilled at sub 1,000 foot spacing, maybe around 700 feet, thereabouts. It varies by unit. 89's Torero unit right here is a unit that we just recently drilled, and even at 1,000 foot spacing, it looks like we're probably just a hair too tight. And also for use as an analog, it hasn't been really producing for long enough to have confidence in what the hydrocarbon pore volume contacted would be for the child wells. So, alternatively, there's a unit that we drilled about a year ago. It's up to the northwest that I'll end up using here as a analog for what to expect from my child wells. Lastly, on this slide, I did want to touch on, and there's probably a long list of assumptions that need to be listed. This is just what I could come up with off the top of my head. These assumptions, this is a fairly simple model, this volumetric model, and it makes a lot of assumptions. But I think that as long as they're understood and accounted for, I think this is a good way to still backstop an analysis. Okay, so this is the unit I was referring to, the 89's Prairie unit up in 4 North, 4 West. Let's start with the parent analysis here. I was able to get a pretty decent match for the on the numerical model, which I don't show here, but the child wells are still pretty complicated to do even after a year in the numerical model. So I switched over to using flowing material balance. This, one thing I want to point out is just for how long this curve continues to flatten. This well has been producing for well over 1,000 days, and you can continue to flatten that slope. So it makes, again, it's going to make comparison to child wells fairly difficult. So these are the 4 child wells that were drilled. It's at about 1,300 foot spacing. Because that value of that slope that I showed on the last slide was so much higher than the child wells, and it doesn't really reflect what's happening with the EUR, I ended up just taking the slope of the parent well at the exact same point in time, kind of under the assumption that the child wells are probably going to have that same tendency to break over time also. And I do this to just get a simple estimate of what percentage drop is there in the child well contacted pore volume compared to the parent, and on average it's about 63%. Okay, this is the slide I'm going to refer to my notes for sure. All right, so now we're going to get into some equations to help pull it all together and determine how many locations are left. So first, we have to determine how much pore volume remains. That's going to be the total mapped hydrocarbon minus the parent contacted hydrocarbon. Our child well expectation multiplies the 63% average that we just got from the Prairie unit by the parent's contacted hydrocarbon pore volume. If we just divide our first equation by the second, we will end up overestimating the max locations. And that's because, as we can see from the Prairie unit over in this table to the right, we don't actually end up contacting all of our hydrocarbons. The table on the right has the Prairie map versus contacted pore volume, and we see that at 1,300 foot spacing, we were able to contact about 75% of the pore volume in the Woodford. I call this, and I talked about this a couple of years back, the completion efficiency factor, and it's pretty similar to a recovery factor, but for mapped hydrocarbon instead of contacted hydrocarbon. And that number likely increases or decreases as you drill more wells, and you're just more efficient by brute force. So remaining pore volume needs to take this into account for the parent well and the child well expected pore volume. It needs to have that term added as well. So to sum up, we can follow this little flow chart here at the bottom. We calculate the true remaining hydrocarbon pore volumes. We estimate child performance inclusive of our efficiency factor. And then we divide the first by the second to get a gut check on the total number of wells that the unit can fit in addition to the parent. I think this is really something that can help in situations where you have prolific parent wells, and you need to take that into account, especially in a setting like ours, and also in areas where you have rapidly changing reservoir volumetrics from unit to unit, which is certainly characteristic of the Woodford and Mississippi. So I won't go through my workflow again. I talked about it at the beginning. Some improvements that I think that could be made to this. Obviously, the addition of units that we are drilling and the data that they'll provide over time is going to help to calibrate this, both from the expectation of the child compared to the parent, as well as that completion efficiency factor. Let's see here. The other thing is that the non-uniqueness is very high. I think that one thing that you could do is probably implement something like a Monte Carlo simulation to really try to get a sense of how much the different factors that you've assumed, or the different assumptions you've made in here, might affect the final answers. But in the end, as I said before, I still think this is a good just gut check on making sure that you don't overdrill your unit at least. That's all I've got. Thank you.
I actually have a question for you. If you go back to the efficiency point, just one second. So I remember when you presented us a couple of years ago, you showed us the month, and I think on one case we had more than 35% of it. Now we're within 75. What has changed?
I haven't done that analysis, but I would just automatically assume that that's just because we're dealing with so much more gas here than those units that I showed in the past. Those were definitely like true volatile or black oil reservoirs. And so the recovery ability in a gas is obviously going to be a lot higher.
Any questions?
Yvonne, sure. Have you done any geochemistry to see what the source of that gas is? Because anytime you have a greater EOR than you would expect, it's because you have to be engaged with a different layer. Geochemistry would be a good place to start.
Yeah. I've seen geochemistry in the past at a different company, and for sure and even in an area that wasn't affected nearly to this extent, it still had what is it, hydrogen, I can't remember the hydrogen 3 or something that was indicative of a much more mature source. So and that's just kind of always undergirded my understanding of the Woodford, is that that's just present throughout. And so any variation of that, I've always just gone right to, that's a deep basin gas that's managed to migrate here. And I think that just by virtue of being in a setting that's so faulted, that you're just able to, it's kind of present in those faults. I don't know if any of this all makes sense, but it's present in all those faults. You frack a well, you're able to reach out very far and access all of that gas. I don't think that it is coming from a formation underneath the Woodford. I think it's actually present there in the Woodford. We have a lot of examples of drilling Mississippian at the top, in the middle, and the Woodford, and the GOR, what's it called? The gradient of GOR. You see black oil at the beginning, and you start to go into drilling a gas by the time you get down to the bottom, and it's a nice smooth gradient. Thank you.
So for the folks online, the last question was just answering if it's seen some geochemistry to back up the kind of migrated gas piece. So the second to last presentation before we're going to do our PM break is by Stephen Young at Devon. It's about evaluating refracts in the Eagle Ford. It's a paper that Trevor himself and I presented also at Irtech. So with that, Stephen, I'll give you the floor.
Perfect. Appreciate it, Matthias. Let's go ahead and do that. So to kind of kick off the start here, most of this work was certainly done by a colleague of mine, Trevor Stokes. So I'll go ahead and just claim all of it as myself. Unless you have any questions, then we'll kick it over to him. But what we'll largely be working through today here pretty quickly is a workflow that we did pretty early on, the first time we were really digging into this flowing material balance, multi-phase flowing material balance that got put into the software. And I definitely take the approach that Adam referenced earlier, where as long as it works and it gives me a result that's repeatable, then I'm not as worried about the data and the science that sits behind it necessarily. So we kind of were going in blind and agnostic as to kind of all the details behind it, but wanting to see, hey, can we start getting some trends that can fit early time performance predictions to the EURs that we're seeing with an uplift associated with a refract. For us, the main reasoning behind wanting to go to that approach is the refracts. Everything I'm going to be talking about here is our Eagleford acreage for the most part. And refracts are frankly pretty hard to forecast with DCA when they come on. Lots of complex properties happening in the reservoir, different pressures that you're associated with, different flow regimes. And so you get a lot of kind of a bit of a horseshoe often at the bottom of production, and it flattens out very significantly. And it's hard to predict where that's going to happen. And this workflow actually did a really good job of giving us an answer within 30 days of well coming online to be able to give us a quick swag at what we think a reasonable expectation for the well is. So what I hit on just a minute ago was, taking kind of that more big data approach and throwing a bunch of wells at it and seeing what trends actually came through in the data. And frankly, it wouldn't be possible, at least for myself, to have done that, because I don't want to build up a whole bunch of wellbores and spend a bunch of time making that data readily available. Fortunately for us, we do have the Snowflake integrations. All of our data is automatically getting pulled out of WellView and our other softwares. All of our wellbores are already built for us. All the production data is coming in, directional surveys, all the data we need for our PVT calculations. So we've got 4,000 wells readily available at our fingertips now with all that data collected and all the pressures calculated and able to hit these automated workflows really quickly. So for someone lazy like myself, that's been a huge game changer for us. Otherwise, I never would have done this. So I'm jumping into multi-phase flowing material balance quickly. I'm not going to talk through any of the science whatsoever. There's way better people in the room for that. But I do want to talk about what a little bit is unique with the Eagleford. For us, there's kind of three different scenarios when thinking about early OOIP that you can calculate versus late OOIP. And so certainly the standard of what you see is that initial fit is very small OOIP at the beginning, just like Brian was showing, and it curls over and continues to curl as you move further and further into infinite acting and starting to see boundaries. You get higher and higher OOIPs. There are certainly scenarios where early OIP equals late OIP. That's the dream world where you can get an answer really quickly, and really you only see that largely in overpressure black oils, or at least volatile oils. So that is really fortunate when you have that world. What we have in the Eagleford is number 3. Our early time OIPs are quite large, and our late time OIPs are very small. And what that is associated with is really strong geomechanical effects that we have in the Eagleford and stuff just closing off on us over time. So I'll show one example of that quickly, just kind of set the stage of what we're dealing with. So the first plot you can see is zoomed in really tightly. I think that number there, we're sitting at 600 flow material balance days here. And the next slide, I believe, is 50,000. So massively, massive different scales that you're here, sitting here on the left versus the right. And an original OIP of 2,000 with a wait time of 600. So for us, I'll say everything, all the workflow I'm about to talk to, really focused on that early time OIP. If I'm waiting till these wells have been producing for years, well, then I can just use DCA. I don't care about it at that point. So I'm really focusing in on that early time. First 30 days, what can I get out of this data? So one of the first wells we looked at, I of course wanted to go look at a successful refract and see if I could see that increase in OIP and what does it correlate to. So on a DCA world, here's an example of a well prior to refract, we were forecasting at 300 MBO. Following the refract, we were at 575 MBO. So almost a 2x increase or a doubling of our EUR associated with this refract. Then we look at the early time OIPs. We got 900 early on. And then if I look at just the first 15, 30 days of production when the well came online the first time, and I got 1900 when I do following the refract. I said, huh, okay, that's actually pretty interesting. That's almost, the same number here, kind of a multiplier. And I went ahead and did the workflow quickly for the late time too, and you see that same sort of trend still holding true, moving into late time. And it's certainly something we're thinking about can we start using this as more EUR predictions and things like that, other than just a refract uplift. But it was super nice early on to be able to say, hey, I know what my early time OIP was, and I know what that EUR is associated with. Then I do the refract, I know what my new early time OIP is, and I'm just missing that fourth number that I need to solve for, which is that incremental uplift in EUR. So I said, okay, that was pretty cool. Does that work when I look at an unsuccessful refract where, yeah, we had some acceleration, but we didn't add reserves? Is the science and the math here going to bust? And it's just because my increased pressure and it just happened to be a coincidence. So I pulled up an unsuccessful refract where we got a lot of nice acceleration out of it, but didn't add a lot of reserves. And it actually came in as you would wanted to have hoped it had. Early time IP from primary depletion and post refract were almost exactly the same, giving you that same trend. So even though my late time OIP had fallen back off, that early time above bubble point, able to see kind of that full extent, had a similar trend. So I thought that was pretty cool. Called up Matthias and said, hey, I don't want to get into the math of this. Is this complete nonsense and sheer coincidence on these two wells, or is this how this workflow would actually make sense? So he popped up a quick simulation case, threw in a well bore, threw in some refracts, put in some new fractures, such that he got 2 times his oil recovery, and threw it over to material balance, flowing material balance. And it says, yeah, actually, if you double your oil production, when I built the simulated case, that is what it would look like in the flowing material balance. I said, so he said, yeah, you're not completely, moronic. There might actually be something here. So we took it a little bit further. Like I said, we have a whole bunch of wells at our disposal. So the first wells were pulled up here were 29 refracts that we had done in the Eagleford, and compared the early slope OIP pre-refract to post-refract. And we had about an 80% increase in OIP from the very initial primary depletion OIP to the post-refract OIP. And then we did the same thing with the late slope and said, hey, that's still trending out late time for that same sample set. Went ahead and mapped it against our percent increase in oil, and then it mapped out really pretty well with pretty decent correlation, showing that, hey, this is a workflow that's been pretty consistent for us, such that now when we do have wells come online within 15 days following the refract, we can go do this workflow and start to get a pretty decent feel for how successful of a refract was that, which has really been super helpful for us, and especially when we're trying out different types of refracts and different spacings and different types of techniques. Being able to get an answer 15 days after the well coming online has been pretty tremendous. The last thing I want to pull up quickly, just because I thought it was cool, we do have a well that we pumped radioactive tracer in the initial completion, so back in 2009. And then we did the same thing when we did our refract back here in 2023, which was a cemented liner. So you can see the statistics at the bottom as far as what we had before and what we had afterwards. And what we saw was pretty surprising to us and pretty encouraging. So my expectation going in was certainly the previous clusters, significant depletion associated with those clusters. We really thought that those are going to completely take over and take all of our proppant and all of our fluid and just suck everything that way. What we saw was actually, if anything, kind of the opposite, where we had a previously stimulated cluster, obviously very wide cluster spacing historically, 120 feet. If anything, we actually slightly avoided that area. So that was really nice to see that we were able to get really nice coverage throughout the lateral. This is just a couple random stages I tossed in. Being able to compare that, hey, we're getting nice isolation with our cemented liners, and as well, we're able to avoid our previous depletion, access new rock, and thus are able to get, that 2x increase in production is really hitting a lot of new unstimulated rock. So that's been pretty exciting for us and has worked out well. So yeah, just kind of in summary there, we're starting to get to a workflow now that we feel comfortable with 15 days of production, starting to give a quick look at how successful these refracts are. So it's been a pretty awesome workflow for us, and appreciate you guys taking the time to listen.
I promise I'm a difficult question.
All kinds of commonalities, pioneering. Thank you, Justin. One question I have for you, we have actually used what you do paper and it is methodology for some of the projects that we have. So it is working, that kind of thing. That I'm curious about your thoughts on, when you do refract or kind of a well intervention, it's the same reservoir, the average pressure is more or less the same, so you can use FMD because you don't really add the energy to that. But you always struggle using a similar technique for practice. Have you tried to use it for kind of quantify practice? I know things are about a quarter of them are good, 60 of them are neutral, maybe a quarter of them are bad. But it's management to quantify or for research purposes, argue how bad it is. Do you use it for that?
Yeah, so that's super interesting. So the question is basically, are you able to apply a similar methodology for looking at frac hits and seeing success with that, particularly in the Eagle Ford? Short answer is we have not looked at that at all. Super interesting question. Definitely something I'll have to give a shot. It looks like Matthias might have a comment there, but.
I was about to ask you in line and some of the share that also was actually they brought a couple of things. So the question was, we do the same analysis on water being impacted by an offset flash. Yes, we don't have the kind of geomechanical that we have in the Permian Basin. So in the Permian Basin, that's what the 15 months I've looked at it. Those two basins are definitely, yes, you can apply the method to determine, that's our go-to technical process for knowing, hey, have you lost the tank post an event? Can you repeat his answer online?
Yeah. So basically his answer was yes, this has been a workflow that they have used in the Permian Basin and Marcellus, I believe he said, to see if that tank size has shrunk post-refract. And he said, yes, that has been a successful workflow. That is their current ongoing workflow that they'll use for that kind of wells.
Yeah, I'm sure they did real quick. I'm just curious, we get 15-day decision or monitoring station, what kind of decisions can you make that matter? How does it compare to what you were doing before, where you're not knowing for, you're waiting on 6 months, 100 days, 6 months? What were you looking at prior to this?
Yeah, so the question is, now that we're saying we can, start getting that first estimate within 15 days, the question was, what were we doing historically? How long did it used to take? What kind of decisions is that impacting? Probably 180 days is a reasonable guess. Kind of saw on one of those first slides, we tend to have a bit of a hockey stick. Every well was doing that at a little bit of a different time. So it was a little hard to predict really when was a good time to be able to give the thumbs up or down. But yeah, 120 to 180 days is probably a reasonable number that before we'd feel comfortable in the success of a refract. And with us, with how quickly we could be going through this program, certainly any changes we were making as far as switching from bullheads to cemented liners, the amount of prop that we're pumping, how tight our cluster should get. This certainly was helpful just to make those decisions and impact a lot more opportunity as opposed to having to wait 6 months before finally making that decision.
Excellent. I know there were some few other questions there, but Stephen, he has told me it's going to be very approachable in the bar if someone buys some drinks. I don't know if there's any finance fans out here. I've been on this Warren Buffett frenzy in the last month, and maybe that's because we had a similar lifestyle and just sit in a chair and talk. But I really love Braden's title. It's a play on seeking alpha, which is like a finance blog or something. And it's about fractional RTS. It's really relevant for those. It's kind of an internal joke for those guys. Braden won the Effective Award last year, kind of the inventor and the original co-author on that paper with James on numerical assisted RTA, which is the foundation of a lot of the stuff we do in the software. So with that, Braden, floor is yours.
Thank you all for letting me present today. So I'm going to walk through kind of the outline of the presentation with also the conclusions in gray, so you kind of know where I'm going. But we started out with trying to apply our numerical RTA to anything that's non-uniform. So numerical RTA was classically built for uniform models. How can we extend that? It's actually really easy, so that was a big plus. I think it's better than looking at it analytically when we're looking for anything that has multi-phase effects. So I'll look at why, kind of if you're just looking at it analytically, you could potentially get an answer that looks more non-uniform than the numerical answer would give you. When we look at, do we actually need that to match our Midland Basin wells? We were intending to try to look for which wells had that more non-uniform completion. Is there any trends to those? How could we predict that? How could we optimize that? Surprisingly, we didn't need it for very many wells, so we'll get into that, and that's still something that we're thinking about internally and don't have a lot of great answers for. Point number 4. And then number 5 is, even if you're not willing to kind of go through all the numerical work for a field, which wasn't a small amount, what are some of the kind of signs or factors that you could look for on a very high level? And really it's that GOR is kind of the main one that popped out to us. So I'll show you kind of what we look for now when we're just looking at other fields to see if we see any signs of that. So I'm not going to go very much into this, but I do refer to this in almost every slide. So I just want to give a very brief description. So classically in RTA, we're assuming all the fracs are the exact same length, the exact same height, and then that they're all evenly spaced. I don't think anyone would stand and say we believe exactly that that's going to happen. So fractional RTA was a form that you could say, if we have some version of complexity in that kind of middle diagram, or if we have difference in clusters going off, how can we kind of quantify that and look at that? You can also think of it as XFs that are different lengths. So really what I'll be referring to today is anything that's uniform is going to have a delta of 0.5. So I'll try to say uniform or delta 0.5. And anything that's not uniform, so you have some unevenness, is going to be a delta factor lower than 0.5, with the lower being the more kind of non-uniform it is. So 0.0 would be super non-uniform, 5 is uniform. So probably like everyone, if we ever have people do frac wells, we get something like the top left, which would again suggest something very non-uniform. In my mind, we can kind of approximate something like that with the diagram on the bottom left, where maybe we have different blocks of the reservoir that are being drained at different speeds. So some of the reservoir is close to the fractures, some of it's very far. And if we think about that in a numerical RTA sense, we're already running a whole bunch of different models that hit their boundaries at different times. So that kind of middle diagram with the 30x by it, that one probably will, the pressure transients will go out and they'll never hit their boundaries within a 30-year period. So that's our infinite acting one. And then we're running those different cases, and in the traditional numerical RTA, trying to see which one matches the best. But there's no reason why we couldn't just take those numerical model runs and add some percent of each of them. So that's what we're going to kind of do with this next one, and I think it's being built into whitson Plus, is that you can have a distribution, so you can have X% of the first one and Y% of the second one, and kind of add them all up together with adding the oils, adding the gases, to kind of get that what that blended combination would be. So that was what we were using to kind of take the traditional numerical RTA and be able to model a system that potentially has fractures that are hitting boundaries soon, and other fractures or other parts of the fractures that are not hitting the boundaries at the same speed at the same time. What this kind of looks like in practice, if you're trying to visualize it, is the models that don't hit their boundaries for a long time. The oil rate kind of stays in higher relative to the others for longer periods of time. This would also be synonymous with kind of a B factor of 2 for the whole period. And then going to the other end of the extreme, if you have a fracture that's hitting the boundaries really quickly, the oil rate's going to start off high, it's going to die really quickly, And then we're going to be adding the oil rates from each of those mols, again, in a certain percent. So Mr. Acuna created the delta parameter that defines a distribution. So if you pick a delta value, it gives you, it says this many ones with a, that are going to hit a boundary for a long period of time. And it gives you a number for each of the sets. So that's the one we're going to focus on today. But we also tried to build it in our workflow that you could have different distributions. So when we do a frac model like this, we could export a distribution of fractures and see if that distribution matched better. And then we also allowed it the ability that it could just history match. So algorithm could go through and try to find the best distribution. We knew that this would be pretty dangerous, but maybe if we saw a whole bunch of wells fit with some distribution, it would teach us something about the distribution going forward. So as a side note, when we're looking at this, why do we have to do this numerically instead of analytically? I'm stealing some slides from Whitson here. But when this is a good case, I think, where they have something it's a numerical model and it's perfectly uniform. But due to the multi-phase effect, so it's a black oil where you're hitting a bubble point and you have multi-phase flow, if you're just looking analytically, you're going to see a delta factor less than 0.5. So this is kind of giving you the wrong value where this model is actually perfectly uniform. The multi-phase effects in an analytical space are going to tell you it's not uniform. And so this would be a wrong kind of flag, I would say, if you're in a situation where you're going to have anything of multi-phase flow, which for me is black oil in Midland Basin, so everything's going to be multi-phase. Now, the numerical model is going to account for that multi-phase impact, so we're going to be able to split what is just the multi-phase piece towards what is actual fracture non-heterogeneity. And as an example of a real well looking at this, the well in green there is 5 years of history with the downhole gauge, so we can be pretty confident in the data. If we're just looking at it from an analytical sense, and again, this is a black oil well, you would definitely say that delta value of 0.3 seems to match better. It matches better early time as well as mid time before we go into boundary dominated flow. And the gray one of delta 0.5 or that uniform model would not be the best fit there. However, when we take it to the kind of far right diagram, where we're looking at it in the numerical RTA sense, then you actually see that the uniform model, the delta of 0.5, matches it much better, the model in gray there. And the model in yellow, the delta of 0.3, doesn't match very well. So this is an example of a well where if you're just looking at it analytically, it would say, yep, this is a low delta, you must have some non-uniformity. However, when we take out the multi-phase effects with numerical RTA, then it actually says this looks fairly uniform. We're going to go with the numerical RTA going forward. And what we're going to do is we're going to kind of set up every well the same. So we looked at 269 wells. We're going to look at the best uniform model fit, which is the dark gray here, and we're kind of judging best fitness based on the LFP in the top left, the GOR in the bottom left, and then the cum volume. So it kind of the error is a function of all of those. And then we're going to compare it as well with a non-uniform model. So in this case, having a delta factor of between 0 and 0.5. We're going to have an algorithm go through and try to auto-match it based on this to try to take out the human element and make it comparable. And then the goal here was that on the 269 wells, we'd be able to identify which wells had a more uniform completion, which ones had a very non-uniform, and then we're going to try to predict that with looking at the number of clusters. Was there things about spacing, any geology effects that we could say these things are predictive of low delta values and these other variables are predictive of high, and how do we optimize that going forward? So we're hoping to see something kind of drive that non-uniformity was the intention, and how we were going to look very smart is what we thought. This is the results of going through the 269 wells. So the chart on the right shows when we apply a threshold, so saying that if we're using delta, it has to be at least a 20% reduction in error. How many wells, what was the best match for each delta value? So as you could see, 95% of the wells matched best at delta of 0.5, so that's the uniform model. This was very surprising to us because I think any of us would say we probably see some degree of non-uniformity. There's a million things that can cause that. Uniform is the far bookend. We would not expect to see that as the majority of cases. And only 5% of the wells matched better with that with the delta less than 0.5. So we was not what we expected, but we did look at, is there anything statistically driving what's in that population of 5%? And there was nothing when we ran the regressions that we could find. The only minor thing was that they were more likely to be a child well, but it wasn't like all of the 5% were child wells, so it was still pretty marginal. And when we looked at the population, it wouldn't be wells that you would pick. So it wouldn't be standalone wells as there, or wells with gel fracts or anything like that that we could have rhyme or reason to. So yeah, very, very surprising to us that you would be able to match it best with the uniform model. Even when we allowed it more degrees of freedom to say, okay, you can have a distribution of anything you want, can you still match it better? And there still was very little improvement there. So it almost, something seems to be making it look more uniform, and I don't have a great reason as to why that would be. So it's still something we're discussing, because when I talk to the people that do the frac models at Apache, they say, well, you can't believe the fracs are uniform. And I say, I agree with you, but our uniform models seem to be matching better. So I don't know what to tell you. Let's have the same chat next week. But in a way, it makes our life easier. If there was this degree of heterogeneity, we would be hopefully trying to predict that, but that's a lot more complexity for our workflow trying to optimize well. So there's potentially a silver lining. It just wasn't where we were hoping to go. Depending on how you pick that delta, so this was a well that the delta of 0.33 did match more than the 20% better. When you look at the black is the actual data versus the gray is the uniform model, yellow is the delta. You can see the delta is definitely a better fit. I would still say the gray one is probably good enough in most cases that we'd say that's passable. But then we wanted to say, what would be the implications if we had a delta value less than the 0.5? So the graph on the top right is definitely the most meaningful to us. That would be the cum oil. So you can see the actual production in black. The gray would be the projection with the uniform model. The yellow is the projection with that lower delta value of 0.33. So if you're looking especially at a remaining recovery, you are going to get quite a remaining recovery difference, plus 39% in this case. However, if you look at where you're going to start to really deviate, it's at the 15-year point in this case. So not something we're going to be able to see within the next year or two, not something we're going to be able to conclusively decide on for sure from the cumulative oil perspective. However, one of the things that seemed interesting to us was that the GOR was much bigger and much sooner, the difference. So the uniform models generally have a GOR that's ramping in time if you're in the boundary dominated flow. But the models with the non-uniform models, so anything less than 0.5, you can have different GOR behavior, generally flatter from what we're seeing midlife to even declining in the midlife period. So that was kind of okay, we can look for this at a high level. And if we see those effects, then maybe that's something where we would want to do the numerical RTA to try to see and capture that non-uniformity. This was a bit of a puzzle as to why that was happening. So I just this is my second last slide to kind of walk through what might be driving that GOR behavior. So I have, again, those oil rates of the purple well is the one that will never hit the boundaries. The red well is the fracture that hits its boundaries very quickly. And essentially what happens, if you kind of look at that middle diagram, is the fractures that hit their boundaries die out really quickly. So they become less of the overall flow stream percent. And after a certain period of time, they essentially become zero contribution to the well. So the well begins to look more and more like the longer fractures, or the fractures that have the most drainage volume that will stay in the transient flow the longest. They essentially become a larger percent over time. So the GOR in the far right one kind of looks like an average at first, but as the red ones start to die out, the GOR actually starts to more closely approximate purple. So you kind of get that GOR that rises and then either slowly rises or in this case falls. And that would be kind of the thing that we're looking for now, is to be, if we're having a large degree of non-uniformity, which any frac model, anything else would show, we should see that in the GOR behavior. And when we look back at our wells, at least in the Midland Basin, we're still seeing the GOR ramp, at least as of this time. So that'll be kind of the thing. I'm also curious to, if there's anyone here that can kind of look at that as a first basis, I think it'd be a good screening, and be very interested to see in a numerical sense, are people seeing the need for that non-uniformity, or are the numerical models and the uniform working well? So just to conclude, the numerical RTA is very easily adaptable. There's no extra runs. Instead of just looking for the best one, you're just using a combination. So it's really easy to adapt that. The analytical techniques will give you about like a non-uniform, they'll say it's non-uniform, but will happen just from the multi-phase effects. So I'd recommend the numerical RTA just to split that and then say this truly looks like it's a non-uniform effect. For us, 95% of the wells matched better with the uniform model. That's been a bit of a puzzle, kind of related to the next bullet. We're not sure if there's something that we're tuning in the rel perm or something else that's making a uniform model match a non-uniform system somehow. Something we're thinking about. I don't have any easy things as to how that would happen or how that could happen. Then it just seems like it'd be a strange that you'd be able to make up for it that much. And then the final bullet point is just, again, that GOR is kind of that early time indicator that you might be able to see within a reasonable time to try to detect are you having those uniform versus non-uniform cracks. So I'd like to thank you all for listening today and be happy to take any questions.
Any questions?
I just have a question. If you've done any post-grad on to compare like uniformity index calculations associated with that in the modeling done?
So the question was, is there anything in that we've done kind of measurement-wise to see if we have non-uniformity? So we haven't really done much on the logging perspective, but we've done offset fibers, and we definitely see that non-uniformity of hits. So we see planar fractures, but there would be no reason for me to believe that everything would be ultra planar, ultra like consistent NF. I would definitely say there should be some degree of non-uniformity in practice. But again, the uniform models seem to be able to match the rate time behavior. So that's kind of definitely the puzzle for us.
I just wondered if we're pretty convinced that it's non-uniform, but the uniform model seems to match the most. Is that telling us that maybe you're representing the non-uniformity in the wrong way? I mean, or there's something about the way the non-uniformity is put in the model that's just not representing the actual cases. Because you do see this non-uniform behavior fibers, but different crack models will predict different levels or different ways of representing this non-uniform. You showed a Refract result that looks like that there.
Yep.
You get a lot of 100% asymmetry. Other models will give you less asymmetry, still variability. I'm just wondering if we're not capturing it quite right, or is there really some fundamental disconnect between what we think the fractures look like and what the models represent, the RT model?
It's a great question. So the question was, is there something that we're not representing in the workflow to kind of, there is non-uniformity, but we're not representing in the right way? Is that a good summary? So I would agree I guess when I think about the degrees of freedom that we gave it here was we could follow that delta parameter down of that distribution, or we could have any other combination. And given that we still didn't see it match that much better, it seemed that it had quite a few degrees of flexibility on hitting any non-uniformity. Part of the things that we've talked about is there something else that's happening, and we've talked about, call it well spacings, where maybe when your fractures go too far and then you're connected to the next well, maybe that enforces a uniformity on you kind of post there. As you talked about for fracture conductivity, we've wondered if maybe the fracture conductivity degrading also kind of makes the end result more uniform than what we would start as. The final puzzle piece related to that for me is even when we had a 0% threshold for improvement, only 30% of the cases use some form of that, which to me is, even if you allow it to have some ability to just match noise, I would have expected 80, 90, 100% to use that factor. So it almost seems like there's something pushing it the other way. So I would agree there's more to it, and that's why we're kind of puzzled as to why we're not seeing it in this, but we obviously don't think it's perfectly uniform either.
Okay, first question though. The second one is, how are you defining improvement into your model? Is it just primary phase, or is it secondary phase, which will be some matching of secondary phase? And the second one is the development.
Yep, so the question was, how are you defining the improvement? So what we're doing is we have a kind of a mean squared error with capped out for outliers, and it's trying to match the LFP, the GOR, and the cum oil and the cum gas as a combination. And then we're kind of saying, what is the error, the total error of those given the uniform fit, and then what is the better match with the, call it, non-uniform model, and looking at that error and saying, you have to reduce it by 20% for us to call that meaningful.
And the second one is, on the in chart when you're showing like 30% difference between a delta and 0.5, how is it that you cannot see any performance difference between those two deltas when we know that a 0.3 delta will be the higher speed of a chart of design versus 0.5 is going to be lower speed and less design? So why do you wait 15 years for the difference?
Yeah, so the question was, if you have a delta value that's lower than 0.5, shouldn't you see that sooner in time? And it depends on how your distribution looks for sure. So in this one, I would say because it was so constrained for that early time, you can see there is a difference of the yellow model. It does have that slightly higher value at the start. I guess if you only have a little bit of history, I could see more divergence. So it's probably if you have a well that already has 2 years of history and is matching there, that part is constrained. As you said, the delta should start at a higher value, decay quicker. That causes the GOR to bump up higher and then stay flatter. So I could see it at either a delta value of lower than that, or depending on how you have your largest tank size set up, that could be an impact there. But this would be, I guess, given the constraints for this well to match best, there wasn't a huge difference in that early time.
All the other questions answered already.
Perfect.
Great. One question had, the cases that you have to run to make the weighted distribution. Does it matter which cases you pick? Is there some kind of a recommendation I've seen about which practice cases that you're supposed to run for weighting and how to weigh them? Or can you just pick whatever one you want and then say how to weigh it?
So the question was, how do you find those distributions, I think, for the different OOP sizes that you need to plug into your model?
Yeah, you have to pick a series like the 10 model practices. And then you weigh those according to the formula.
Yep.
So those 10 that you pick, the practices, can you pick those randomly or you pick them in a certain way? The 10 that you're going to weigh with this rule.
Yeah, so it's so we had 8 models basically picked, from ones that were never hitting the boundaries to ones that were hitting the boundaries like very quickly. And so I believe, and maybe this is something we want to talk about further, but with the distribution, it'll lay out if this is your delta distribution and these are the sizes of your tanks, this is the unique percent of each that will satisfy that solution.
I think the question is answered. Very good. I think we'll have to take a break now, so I know there's a lot of questions. I think that was a good presentation. We have a break now at the end of the case and whatnot. And then we'll be back in, I'm going to say 10 minutes, but everybody knows that it's a thing, but we'll be back in 10 minutes.
Everyone will be back here in 10. Okay, we're gonna get started here with, there we go. I can get that ready for you. Do anything for you. There you go. Sure.
Hi everyone, thanks for being here. My name is Alejandro Lers, I work for Chevron and have the pleasure to be invited to analyze this well. When I received the invitation from Matthias, I thought, okay, this is gonna be a bookcase, super easy, quick and dirty, 5 minutes. Well, you're gonna see that this well is a little tricky, at least to my opinion, and then let's see if we can concur here. If this is a competition, disclaimer right now, I'm gonna lose. Okay, so first of all, my disclaimer. Why I know that I do not know. So real PVT, we don't have that. He didn't even give us density. I don't know even what is the API of this well. We only have GOR, initial reservoir pressure, and some other stuff. And then we don't know location, reservoir depth, well spacing, anything like that. And then the operational information validation, I don't have a way to find that out. So my analysis approach was basically two things. First, I'm gonna trust the production data that is there, and I'm gonna let my imagination fly. If it seems like something happened, I'm gonna assume that happened, and that's the way I'm gonna analyze this well. And the second one is, to me, it's not only about getting to the answer, it's about to getting to an answer that I can apply in the right time. What that means for me is like I cannot spend more than 2 hours in a well. So that was kind of my boundary for this analysis. I wanted to spend maximum of 2 hours analyzing this well and getting to a conclusion about that. So what we can see, first PVT, as you can see, initial pressure around, I think it's 5,700 PSI, bottom hole pressure, bubble point pressure around 1,700 PSI, so it's undersaturated, we have a big window there. Now, if we look at our production data, I mean, if you look at generally, it seems kind of okay. One thing caught my attention at the beginning was this part right here, where you see your flow motor pressure, which is that black line right there, going up and then going down, and then your water going up. So then I just dig a little bit deeper there. This is the flow motor pressure again. This is my water cut. And then when I look at it, hey, I mean, to me, this seems like a frac heat. So going back to my rules, I'm going to assume this is a frac heat. If we look at our diagnostic plots, I was planning to use this opportunity to complain about not having my slopes into the diagnostic plots in whitCon, but they smartly implement this right before I got into this stage. So I cannot complain about it, but now we have it. So we see that our well, I have linear flow first, and then it reaches boundary dominated. We're fine there. You know, our bottom hole pressure versus the cum has some strange behavior here. And when we try to analyze what that happened, and I divided colors before and after that frac heat, or what I think is a frac heat. This is what we see. So we see that after the frac heat is when all the weird stuff start happening. So then what I did is, okay, let's go to my flow with material balance. Even if I analyze the wells as if it didn't have a frac heat, this is what I see. But when I see my pressure, my reservoir pressure, my predicted reservoir pressure versus my flow motor pressure, I'm going to notice that my flow motor pressure goes above what it's supposed to be my average reservoir pressure, which shouldn't happen. So then I split this into, I try to zoom in, and see what happened here. And you can see that your slopes start moving around. I'm not always flattening, but flattening and going up, flattening and going up. So that gave me a hint here that, hey, because of this frac heat, I need to analyze this before and after. So I did that, analyze this well before and after what I presume is a frac heat. And what I found is like your before frac heat reservoir volume is around 8,000. Be sure that, yeah, 8,000 reservoir barrels. And after that is 3,400 reservoir barrels. So a huge drop in contacted oil. That's what I'm seeing there. Then I move to my delta values just to understand what we're looking at here. Because my reservoir is still above bubble point, I can confidently use analytical RTA to use this. And this gives me a 0.36 actually. At this point, I should have to stop and say, well, I should model this with a non-uniform spacing fracture model. We don't have that in whitCon at the moment. I just proceed so far, but technically at this point, you should not proceed and try to model this as a uniform spacing because you're gonna overestimate your frac length. That's what's gonna happen. But I did it before and after. I'm trying to stay honest here and showing you your full history match. I'm forcing or I'm inputting oil rate and I'm calculating gas rate, GOR, water ratios, and my flow motor pressure. As you can see, my flow motor pressure seems very good. The initial mismatch right here is just because I cannot predict the initial part of the water rate. Now, if I move to my after frac heat match, good luck matching this GOR. You just don't know where to be matched. I cannot match my initial part of my water rate because definitely I put water into my system and I'm not modeling that way. But at the end of the day, I think this is a successful history match before and after. When we analyze those two cases, you can see these different linear flow parameters all in place, UR, etc. So interesting, you say, hey, this frac heat definitely did something to your well, which is bad. But when you analyze total, though, all the ratios are constant, meaning that, you lost like 64% of your well for that. So unfortunately, I don't have the other well to see if the other well basically produces better, but, that's kind of analysis I have for now. Thank you.
That's perfect. I have some comments on this one, obviously. Let my man Rohit. And that's a fair thing. Like, I'll talk about kind of the problem statement and stuff later, but the engineers doesn't even know what basin this is, so it's a lot of imagination here. But I think it's healthy for people to hear the thought process. It's very healthy. Rohit?
As Matthias said, let's just focus on the thought process and not the actual results. That would be very helpful. I'll sort of summarize the well pretty good. I'm just going to go through the results. In terms of PVT, it's a black oil reservoir, right? GR is 350. Generally, when I've in whitson, when I've looked at a black oil well, it's generally a match has been pretty noisy for me, right? So I had that in the back of my mind when I started looking at this thing. I look at oil viscosity. I would expect the oil viscosity to be a little bit higher than 1.2 centipoise per 350 GR. Maybe I just don't have enough experience in these low GR systems. But I kind of noted that down because that kind of stood out for me. This slide has a comparison of all the different methods and the results that I got out of it. All these different methods, the way I looked at them in silo, right? I didn't look at a single method and use the results from that and compare and basically fine-tune the other ones. All of them were in silo just to see how these different methods compare against each other, right? And if you look at them, they generally compare pretty good. That's DCA, and then that's the numerical model, right? My EUR is in the 700,000 barrel range. And then in all in place is somewhere in like 6 million barrels compared to different methods. Okay, so now if you start looking at it, my interpretation of this was a little bit different than Alejandro's, right? So the green line over here is oil rate, the black line is pressure, the water oil ratio, and then gas oil ratio. Yeah, so there were a couple of events that I noticed, right? You see over here, the oil rate increases and you see an increase in bottom hole pressure. And similarly over here, the oil rate increases and you see an increase in bottom hole pressure, right? So you're drawing these wells down a little bit faster, right? That's what's happening. But at the same time, whenever you're drawing these wells down faster, you see this increase in water oil ratio, right? Which kind of stabilizes, right? My interpretation of that was, you have a low GR system, the viscosity of the oil is probably a lot more than the viscosity of water. So whenever you create a perturbation in the system, water probably flows a lot more freely. So you get that water influx, but through time, there's just not enough water in the system to actually keep that sustained. It comes back to whatever the reservoir long-term water oil ratio should be. Okay, so that's, I'm guessing, a choke bump. This dashed line over here is gas lift volumes. So I'm guessing this is probably just when we install gas lift and you can see the pressure decline associated with it. Okay, I think that's it. The other thing I wanted to point out over here was, based on the PVT, this dashed line is a bubble point pressure. And you can see where it actually hits the bottom hole pressure, right? But the gas oil ratio starts increasing before that, right? So I wanted to see whether that was a disconnect in the PVT or maybe that's some measurement issues going on. Generally what happens is whenever you put a well on gas lift, that's when the volumes kind of go haywire, right? So the gas lift is being installed over here, but the volumes looks fine. The actual GR starts increasing later in time. So I'm guessing there's a slight disconnect between the PVT we're using versus what this well is actually experiencing. Okay, so this is the DCA. Now, in my DCA analysis, again, all of this was done in silos. So this is assuming that all you had was rate data. You didn't have anything else, right? If you just had rate data, and generally an engineer, when they're doing DCA, they're not doing DCA in one well, right? They're probably DCA in hundreds of wells, and you won't have that much. You won't put a lot of scrutiny on these types of analysis, right? So what I did was I just assumed the conservative B factor. In this case, I assumed the B factor of 1, tried to fit the last portion of data, right, and saw what the EUR was. The EUR number came to be, you can see the font is too small, but it was like around $730,000. Okay. Flowing material balance. So again, in this case, I was doing the same thing that Alejandro was. I was trying to match this buildup over here, right? And my slope corresponds to that. And then if you do that, you get an oil in place of, I think it was 5.7 million barrels in place. Okay, now when you get to classical RTA, the classical RTA plot is valid for single phase flow, right? And generally, it's just well supposed to be in linear flow. So I was trying to see when was the area or region of the data where the well actually corresponds to kind of these two behaviors, right? So the plot on the top right, what I've done is I've taken water oil ratio and I've taken GR, and I've plotted it against material balance time, okay? So this is initial cleanup, right? And it kind of stabilizes somewhere around, you cannot see it, the font is too small, I apologize, but it's around like 100 material balance time. And then it looks like GR starts increasing around 200 material balance time. So between 100 and 200 is probably the time period when I think the analysis from this plot is probably valid, right? And that's what I've tried to do over here, right? I've put a line between 100 and 200, right? And if you look at that, that number is like 5.7 million barrels of oil in place. Went to fractional RTA, probably got the same result that Alejandro did was, the delta is not 0.5, right? So it's like 0.23. So that tells you that this well is probably not in linear flow. It's probably seeing some boundary. There's something else going on with this well, right? The fractures are probably not that uniform. So please use the numbers that you saw on the previous slide with caution, right? Because that's what the slide is for linear flow. And then I moved on to numerical RTA. I had a little bit of trouble over here. In the end, I did end up matching it decent, but what I did do was I had to smooth out the bottom hole pressure a lot. Otherwise, I couldn't match it. The couple of things that I do when I start doing my numerical RTA is I'll always start with a very simple model. I'll get my fracture well firms to equal to my matrix well firms, just I want to avoid any complexity. I'll start with no gamma and I'll basically start trying to match and see if I can get a decent match. And then from then on, if once I get a match which is in the ballpark, then I'll start adding the rest of the complexity, right? One of the biggest tuning parameters in this RTA world is well form. Nobody knows what the well form should be. So you can pretty much go with any numbers, right? My rule of thumb is to keep my well forms, these exponents between 0 and 2, or 0 and maybe 2.5. I don't try to diverge a lot more than that, right? For the most part, I've been successful. I haven't had to go and number beyond that, right? One thing I've noticed, and primarily my experience comes from Permian, what I've done is that we generally have to reduce our gas permeability a lot to match the Permian wells, right? And you'll see the endpoint gas well Permian in this case was 0.1. So I started off with that kind of knowledge, and as you can see, the match is pretty decent. In this case, the all-in-place number was like 6.4 million barrels. So once you have numerical RTA match, I just pushed it over to the numerical model, and that's what the match looks like with the numerical model. So it's consistent in all these different cases, right? I don't know whether that accounts for anything or not, but that was my work. Yep. Okay. Thank you.
And what I think is particularly cool here is like how, even though people don't know where the data set is from, right? And it is good points about the PVT, right? There's no tuning equation. This is just default thing Robinson and stuff. A lot of things. but everybody's kind of bringing a little bit of their own bias from the basin that they worked in, a little bit into the thinking. And that's just a general note that I see a lot when we work with different clients as well, and which is totally natural, right? Because there they actually have all the types of data sets backing it up. Good, I'll do a little summary in the end here. Amy, you next up. And I met Amy when she was at Marathon, actually, and now she's with Murphy. That's great.
That's why I got selected for this. Okay, so obviously I'm doing the same well. I'll try not to cover the same background. I think one of the benefits that I see with whitSyn is just in general, it's kind of quick. It's easy for someone like me who doesn't do a lot of RTA. And this well in particular, I asked Matthias, I had best intentions of doing this early. I said, hey, send me the well data. I'll do it ahead of time before I get busy. And he didn't send it. So then he sends it. I go on vacation. I come back. I'm like, oh, shit, I have to do this so I don't look down in front of Rohit. And so, of course, Murphy true fashion, our internet goes down in the building. And I even pasted the email. I was like, I did not make this up. I did this in the lobby of Murphy on an unsecured network. So the screenshots may be a little janky. But, okay, same problem statement. I'll go over my answers at the end. I think it's kind of interesting. I got similar answers on EUR. I got 800 EUR for oil. My OOIP was a little under 7,000. I will say I did this twice. I got one answer. I showed Matthias, I guess, towards the end of the day. And after looking at it, I was like, oh, that half length looks really long. So I ended up tweaking it again and going back. So I think I got similar fits and different answers, tweaking different parameters. When I looked at the production data, a few things stood out. I noticed, I was looking at time and I saw the same thing the other two presenters noted. The water cut went up, bottom hole pressure was dropping. I looked at the dates and noticed it was like end of November, some of these things started happening. And just being a reservoir engineer in a big company, I thought, ooh, end of November, all the management is trying to hit annualized targets. So they said, pull those chokes, get the rate and move on. So that's what I took that bump to be. And then also we had gas lift started and that created a little bit of change as well in the data. So I kind of took those as what was going on, and I, forecast through those points, but didn't put a whole lot of emphasis on my DCA matching those. Secondary products, kind of similar approach. I mean, if you're an asset, you're doing 2,000 wells DCA, so you're not going to spend a whole lot of time matching these bumps. So I kind of just blew through it and said, this is what it looks like. Let's move on to the next model. Bottom hole pressure. I thought this was kind of fun because usually I never have gauge data, and this well did. So that was a win. I said, forget the modeling, we'll use the gauges because we never have that. So I smoothed out some of the gauge data, and yeah, I thought it was pretty good. I did try to use a few of the models. I ended up turning them off, and I used some of the tuning parameters, which was kind of fun, but again, not needed. Flowing material balance. I think when I first fit this, I zoomed in, got a fit I liked, and I saw, I had some issues with that little bump up in the pressure coming above my model. So I ended up tweaking that simulation just to get my slope where I needed it so I'd be above, keep my reservoir pressure above the actuals. Okay, and then the analytical RTA, I think kind of similar fits. I did have a little bit of trouble getting some of the slope boundaries on here, but I do like the colors, Matthias. Thank you. My eyes can see them even when I'm working on my laptop in a lobby. So yeah, very helpful. And then I looked at oil and liquid. I just kind of wanted to compare the answers. Usually everything I do in analytical RT, I'm usually using only oil phase. But I thought it was nice that when I turned on the water, I got kind of similar answers, a little bit larger timed in the end of linear flow, but only about 10 days. So I thought that was neat. One of the things that we did know about this well was the frac parameter. So it was a really large frac. It was like 3,300 pounds, 77 barrels per foot. So I think a lot of that water influx is probably from the frac water. Okay, numerical RTA. I'm trying to think what I started out. There are, when I start numerical RTA, if I'm in a room by myself and nobody's watching me, I will touch every single button. So I was trying to rein it in and say, okay, like let's leave some endpoints alone. Let's tweak things with a little bit more purpose. So I started with my water saturation and got that. That one was pretty easy to line up. And then I started messing with the matrix gamma. I guess you guys can't see my pointer, but the hardest part of getting this well for me, and I think Alejandro said it too, was the GOR. that initial ramp up in GOR was really difficult to fit. I could fit longer term, getting the gas once we're under bubble point pressure, but before that it was difficult. So that was one of the hardest things that I was messing around with, getting like gas saturation points and things like that changed. Okay. The water rate, I think I mentioned, that was one of the first things I changed. Sustained water rate was easy, but the early time, I think with the frac water, you know, there were some things, if we had more time, we could probably understand how that formation water was coming in versus frac water and what we're actually trying to twist and turn in the model. Okay, so this is a zoom out of my numerical model in-time calculations. All the rates look pretty good. One of the things I didn't like was the GOR, but that was kind of in the data set. I think originally we were told to keep it at 350 GOR. So that was just one of the things I noted. If I was going to change anything, I would probably increase that. And I ended up running the sensitivity and kind of like my 400 better. So that would be my next answer. I think that's about everything. Yeah, again, my XF felt a little large, so I'd probably go back into my height. If you're in Eagleford, you know, at XF that large, over 1,000 would be concerning. So I ended up turning it down until I got closer to like the 500 mark.
Awesome. This very healthy exercise. I love how honest people are at this. I'm not used to that. At SPE, everybody saying how perfect their method is and nothing is wrong. But just to summarize a little bit on my end, and here I did one thing in the problem statement that wasn't covered necessarily by the percenters, or at least that I think is really important. So the problem statement was just, you know, estimate LFP, OIP, and EUR, and we gave them basically a lot of consistencies, like the abandonment pressure had to be the same, and the amount of days to forecast had to be the same, etc. But there was one thing I on purpose left blank here that I saw was like either played with or not played with, and that's the use of pressure-dependent permeability. And back to Donish's presentation earlier today as well, some people like to use that a lot. That's a way for you to, for instance, get analytical deltas on the fractional RTA plot that's below 0.5 even though in single phase. So that was something we let be up to the interpreter. So if you go in and summarize the cases of the different interpreters, and I think we agreed that the highest EUR was the winner, right? So I think all on the pre, he had kind of two cases. He was cheating a little bit on that, but the Towson is you're the winner there. So this is kind of the summary. But when it comes to something that important as pressure-dependent permeability, and that's why I think Donish's presentation earlier today as well is very, very, very important, because in areas where at least that seems to be a consensus to include it, and it seems to be just by including that one parameter does a lot of good things for the analysis. There should be more rigorous methods than what we have right now necessarily, or maybe doing that, what Donish said should maybe be what we should do. So that was the average EUR around 870, but everyone in that kind of range. But of course, that would be very different. In the gas case, which I'll go to now, you know, in the gas we have less things going on. It's no multi-phase, and I also said you're not allowed to change the gamma parameter. So that's we'll see how the results change for that. So we're going to switch gears to gas, and can everybody just give a big hand for the 3 on that? The first one on you know, Ryan that you present now, he has become we've interacted a lot. He's a really good guy. I wanted to give him a task, and he was like, "Why did you give me a gas ball? I've never worked gas in my life." This would go fine. I told you that's the easy stuff. So, anyways, Ryan, everybody.
All right, I looked at the agenda and I knew we were kind of at the end of the afternoon, and so I plan on this being pretty quick. Added in a little Matthias humor as well. So yeah, like you said, I'm Ryan Jig. I'm a reservoir engineer for Pioneer, and have just recently started getting into the world of RTA and all this. So I've really enjoyed learning, and feel privileged to be up here. Definitely the least knowledgeable person that's been up on this stage today. But really had a lot of fun with this. And as you said, working Pioneer in my Midland Basin bubble, getting exposed to a gas well was really fun. So he kind of already outlined the task, but he had a couple points of emphasis, right? We're primarily interested in the thought process. Make some slides. We're primarily interested in the thought process. Keep all this stuff fixed, and we're primarily interested in the thought process. So I got it. So this is the most casual presentation I've ever made. I figured why not, our first time presenting at a conference, make it your most casual presentation. And really gonna peel back the curtain on the thought process. So my first step was just, what am I working with here? Gas well, got some weird pressure spikes, we need to take care of that. Be aware of some shut-ins going on. Some kind of significant event down here, offset frac, loading up, not sure. Jumpy water data, is it data problem, is it slugging? And then just also noticing significantly lower water cut than I'm used to in the various targets we have in the northern Midland Basin that I'm used to working in. So that was another piece, like not knowing the whole story of this well was excruciating. Like I've been on the development team for years, and so like, these wells are my babies. I know their whole life story. I know which one had problems, and this is just, I was so in the dark, but it's a really good exercise for me. So start off with DCA, just real quick and dirty, threw in single segment through there. I was like, wow, yeah, never dealt with a well that's cum 12 BCF before. Again, thought process. It's 4 o'clock, let's have some fun. So gas flowing material balance, I just marched down the modules as they sat. And, you know, being a gas well, this seemed to work pretty great. Focus on the late time, smooth stuff, quick lasso fit. But, you know, I don't know, are we in boundary dominated flow? Here's the pore volume and the gas in place. So right around 20, keep it moving, go into multi-phase, same stuff. Kind of focused on that late time, before the significant event, whatever that may be, that kind of caused my pressure to go a little haywire. Very similar, so really low water cut. Then we get to analytical RTA, and this is where, being newer to this, I had to really start thinking a little bit harder. Made my my pick in the bottom left plot, trying to find where that half slope best fits. And so just really quickly, like, thought I had a great fit, was on a roll, feeling good about myself. And then I was like, oh, that's double what I just had. So I didn't know, just confused. And what did I do? I just kept moving. So I said, we'll come back to that. We're gonna come back to it. But let's just keep moving, go down the modules, just like Matthias does in his training videos, and you know, we'll get there. So similar to Amy, I wanted to like start turning everything, and was just playing around, and it ended up being a really good learning experience, playing with this, playing with that, and seeing how everything would change was really fun. But every time I did that, it just made everything so much worse. To where I spent like hours just playing around with it, and that's why I sent you the slides so late. But I just ended up just staring at the computer like, I guess the defaults are right. I don't know. So I went back to the defaults, and you know, ended up with values in this range, and the gas in place being closer to my material balance number. So right now, like, the analytical is the outlier. It's like, okay, let's come together, maybe, and let's just keep marching. So we import that into the numerical model. Initial run, pretty zoomed out. It looks like a decent fit, but you know, it's going to be pretty similar to my numerical RTA. The cum fit was okay back there, so expecting a decent fit over here, get an EUR around 19. But we lay it all out, analytical is still causing question marks. I can't just walk away and like say I'm done. So yeah, something's not right. Let's go back to the visible confusion and dive in a little bit deeper. So just started asking questions, talked to some of the technical peers around me, and just was curious what they would think about. So just like, okay, that's quite a long time to be in linear flow. And then I looked at the frac length that was twice that of all the other modules. And then we're looking at the pressure normalized rate curve, and instead of like everything being kind of that concave down, there was this little section where we had like a little hump or a little saddle or whatever you want to call it. So just observing that was different and interesting, and kind of realized as I zoomed into that plot more and more and kind of explored, I was like, let's revisit that half slope pick. So there were a few different justifiable picks that you could have made as I zoomed in. You know, here's one, brings our A root K up, our gas in place down, which one's right? You know, we're seeing some kind of compound linear flow where you've got, you know, multiple things going on there. Here's another one, gas in place goes up here. You know, again, I feel like I could justify a few of these, just this is where I would need to call in some technical experts and get some more education there. So again, the thought process. So then I was like, okay, I didn't really change much on my numerical model. Let's go back to that. I changed the control on gas and work on the bottom hole pressure match. I was just able to see the mismatch better that way. And I just changed that. Here's that run of that. Didn't change my EUR very much. But then just started playing with a couple things there, and was able to tweak permeability a bit. I wish I knew the well spacing to guide that XE value and understand that. But ended up, you know, running with 19 on the EUR, which sounds like it's on the low end, so I'm gonna lose. But thanks, it was a lot of fun.
About the thought process. That's great. Hopefully that doesn't become my shtick now. That everybody's like, yeah, the thought process. I know how that works. We have two more left. But absolutely very cool. A lot of things to talk about that. Like the analytical RTA stuff, what people have to realize there is when people resolve an LFP in a contact of pore volume, they use constant PVT properties. So the PVT, it's not the multi-phase in superposition, but the PVT changes and superposition is even there not handled rigorously when it comes to like resolving parameters and whatnot. And it's very easy to prove in a simple numerical model in a single phase gas. That's talked about by, you know, Agarwal and was it pseudo-time and that paper and whatnot, but that's a different story. My man, Brian, are you here? Brian is known for having really nice slides, and I'm a sucker for nice slides.
Where?
And I think it's kind of hard to follow Ryan. That was a really good presentation, good thought process for sure. That's similar to what Ryan was saying. That's it's amazing, and what Matthias was saying, that we spend so much time in our basins, comfortable with the reservoirs that we work, that this was actually a lot harder than I thought. I thought gas well was going to be fun and easy, and then when you walk into it and you don't know anything about the well except it's a gas well, and that's kind of about it. That you realize how much you use as a crutch for just basic knowledge, general knowledge, and it kind of all went out of everything, and I felt like I didn't know what I was doing anymore. But so Matthias did say this would be super fun and that we'd really like it, and it was really good last year. So I kind of just dove in, And I think similar to Ryan, and as the gas well is just a little more simple than the oil well examples, but a lot of the same observations that just a really heavy drawdown at the start part, the very flat gas production, the buildup time periods that you see that the pressure spike above the original initiated pressure that I originally called this a frac hit, then dialed back my language later in the presentation, called it a well event, since I'm not really sure what's going on, but the shut-in time period, change in the water production. So there's just a little concern there. And then did start to realize that Matthias definitely chose this well because it makes it very hard. The analytical RTA definitely is the problem to it, but just was going to feel pretty uncomfortable coming in with your production immediately after well event, not knowing what was that well event, what was really going on. So was nervous proceeding before we did anything else. But so standard stuff was not going to show you guys my DCA plot, but just used a 1.0 B factor, got about 24 BCF for the well. Similar to Ryan, it's kind of like, holy crap, it's already produced 12 BCF, and I don't think I've worked on a well that's produced more than 10 BCF in most of my career. So a little intimidating to think that you're going to recover another 10, 15, 20 BCF on anything that you're going to do. And but did feel comfortable. We'd already seen a lot of pressure draw down, a lot of reservoir response to it. So I thought the fun was about to begin. Flow and material balance was pretty easy, but also a little concerning, not seeing really kind of any impacts changes towards the tail end of production life. So very long linear flow time period. And that's kind of, again, going back into with the forecast being the important part. It's not really sure where the long-term forecast was really going to drive and really go. Off of here, I'm usually used to seeing a little more indication here, help you better identify your linear flow time period and really get comfortable for your long-term modeling. And ARTA did the exact same thing previous person did. That's kind of picked the very long linear flow time periods, identified the TL time periods, did observe when you start finding that unit slope where